In the beginning of human thought, the question of light was not one of numbers or of science, but of wonder. People saw the rising sun spill gold across the horizon, and they saw fire leap from dry wood, and in both of these, they believed they touched something divine. Light was life, it was warmth, it was vision itself. To understand its nature seemed beyond mortal reach. For many centuries, it was simply assumed that light did not move at all, that it filled space the instant it was released, an immeasurable gift arriving without delay. Among the earliest voices to wrestle with the question was Empedocles, a philosopher of the 5th century before the Common Era. He imagined that the eye itself was a lantern, sending forth rays that struck the world and returned with information. If vision worked this way, then surely light had to move outward. But he insisted the motion was so swift that no human sense could register it. In his telling, the world was alive with invisible fire, with a cosmic pulse rushing faster than thought itself. The notion was poetic, but the experiment was missing. No one could say whether light truly moved, or whether it was born everywhere all at once. Aristotle, who more than any other defined the intellectual world of antiquity, rejected Empedocles in favor of a view that light was simply the presence of the transparent medium in its perfected state. For him, there was no question of travel or delay. Light was not a moving substance, but an actualization of the potential to see. When the sun rose, the atmosphere was filled instantly with brightness, and the eye required no waiting. In this conception, speed was irrelevant. The language of velocity belonged to falling stones or racing horses, not to something as pure and incorporeal as light. A generation later, Euclid approached vision in a mathematical way. He drew lines from the eye to the objects of sight, and in these lines, he developed the first geometry of optics. Angles of reflection, straight paths of rays, the predictable bending of sight around mirrors. All of this he wrote down with the rigor of a geometer. Yet nowhere in his diagrams did he mark a speed, nor did he ask whether the ray reached the object in time or in an instant. It was enough for him that the lines were straight, that they obeyed rules of geometry. In a world where the speed of light could not be grasped, geometry was safer than measurement. These ancient convictions settled deep. If the greatest minds of Greece believed light was instantaneous, the idea carried forward for centuries, like a stone embedded in the foundation of thought. Roman philosophers repeated it, medieval scholars adopted it, and with every passing age it became more like common sense. After all, who had ever seen a delay? Lightning flashed, and thunder followed long after. If sound clearly took time to cross the sky, then the absence of delay in light seemed proof that it was infinitely fast. And yet, not everyone was satisfied. In the great flowering of learning in the Islamic world of the 10th and 11th centuries, Ibn al-Haytham, whom later Europe would call Al-Hazan, began to argue for a different picture of vision. The eye did not emit rays like a lantern. Instead, light entered the eye, reflected from objects, and formed an image within. His book of optics described experiments with lenses, mirrors, and apertures, and it placed vision on a firmer scientific ground. Still, even here the question of speed remained untouched. Whether light shot into the eye with a finite pace, or whether it existed everywhere at once, was not something that Al-Hazan could measure. Medieval scholastics in Europe translated and debated his works. Roger Bacon and later Witello carried forward his ideas, discussing refraction and the rainbow. But in their pages as well, the speed of light was more a curiosity than a subject of serious inquiry. Some speculated that God alone knew such mysteries, that the finite or infinite swiftness of light was beyond human reason. In the candlelit cloisters of universities, students argued about the angels on the head of a pin, and among such debates, the true nature of light drifted like smoke in the rafters. half considered, never proven. When the Renaissance arrived, new precision in lenses and telescopes began to transform the way scholars thought about light. Johannes Kepler, writing in the early 17th century, demolished the old idea that rays left the eye. He showed that the geometry of vision required rays to enter from outside, focusing on the retina like an image painted upside down on a canvas. With this, he gave the world the first accurate model of how we see. But Kepler too assumed that light moved without delay. His interest was in the shapes of images, the distances of focal points, the geometry of perspective. For him, as for Euclid, geometry ruled. René Descartes, bold philosopher of method and certainty, took a different turn. He imagined light as a pressure wave traveling instantly through an all-pervading ether, much as sound travels through air. To him, the absence of any measurable delay meant that light must move infinitely fast, though he still gave it the language of transmission. In his grand mechanical philosophy, vortices of ether carried planets and transmitted forces, and in this universal machinery, light belonged as an instantaneous messenger. His reasoning was elegant, but once more, it lacked the weight of observation. It was Galileo Galilei who at last dared to test the idea. Standing on hills outside Florence with a trusted assistant, each carrying a lantern covered by a shutter, he attempted to measure whether light required time to cross the valley between them. The scheme was simple. Galileo would open his lantern, and when his assistant saw the flash, he would immediately uncover his own. If light took time to move, then Galileo would register a delay before seeing the return. But no matter how he arranged it, no matter how quickly they worked, the return always seemed instant. He concluded only that if light had a finite speed, it was far too swift to measure with his method, and over the distances available to him. This experiment, half comic in its futility yet heroic in its intent, marked a turning point. For the first time, a great mind tried to bring the mystery of light into the realm of measurable physics. The attempt failed, but it left a haunting impression. Light might yet be finite, but if so, its velocity would be greater than anything known, greater than the fastest arrow or the swiftest cannon shot. The human eye could not catch it, nor could the human reflex respond in time. The valley was too small, the lanterns too crude. And so, the centuries up to Galileo ended much as they began, with the speed of light an unanswered riddle. The conviction of Aristotle and Descartes that light was instantaneous still carried the weight of common sense, but the seeds of doubt were planted. Kepler had mapped the geometry of vision, Descartes had woven it into the fabric of his philosophy, and Galileo had reached out with an experiment, however flawed. The question lingered, suspended between faith and reason, waiting for the skies themselves to provide the next great revelation. In the centuries after Galileo, the riddle of light speed still refused to yield. The ideas of Aristotle and Descartes weighed heavily, but restless thinkers began pressing again at the edges. The medieval heritage was not only a chain of repetition, but also a seedbed for more precise ways of asking the question. In the Islamic world centuries earlier, Alhazen had described the way images formed on the retina and had insisted that light traveled in straight lines, a claim he supported with clever experiments using pinholes and mirrors. His words filtered slowly into Latin and reached the universities of Europe. By the 13th century, Roger Bacon could declare that optics was the most noble of sciences, though even he could not say whether light darted through space or sprang into being everywhere at once. Later scholars in the Renaissance returned to Alhazen's experiments and began to see vision in a new way. The growing craft of spectacle making had already shown that glass could bend light, enlarging or shrinking what the eye perceived. When Kepler studied these devices, he realized that light could be treated like geometry in motion. The eye was not an emitter, but a receiver. a dark chamber where an inverted image formed on the retina. The rays of light crossed at the lens, carrying with them information about position, shape, and color. Kepler had finally set vision on a physical footing, yet he did not trouble himself with the speed. He assumed it infinite, or at least so fast that no practical distinction could be made. Meanwhile, Descartes imagined light as a kind of push transmitted instantly through a universal medium. To him, the ether filled all space, a subtle substance that carried pressure waves faster than anything else in existence. The failure to observe any delay confirmed for him that light acted not like sound, but like force, a transfer happening without measurable passage of time. In this way, he aligned the philosophy of light with his broader mechanistic universe. Planets were swept along by vortices in the ether, while light leapt across space like a jolt of contact felt without any interval. His conviction was unshakable, though again, it was more reasoning than proof. The growing precision of instruments emboldened experimenters. Galileo had already shown that the telescope could overturn the heavens by revealing moons around Jupiter and mountains on the moon. If such a simple tube of glass could expand the boundaries of knowledge, why not apply it to time itself? Thus came his famous attempt with lanterns. On a clear night, he stationed an assistant at some distance, perhaps a few hundred paces. Each held a shuttered lamp. Galileo uncovered his own, and the instant his partner saw it, he was to open his lamp in reply. Galileo watched closely, timing the interval, hoping to catch even the smallest hesitation in the return. But none appeared. The exchange of light was as immediate as thought. The result frustrated him, though he tried to save the experiment by suggesting that perhaps the distances were too short or the human reflex too slow. If light did move, he reasoned, its velocity must be greater than 10 times or even 100 times the speed of sound. Beyond that, he could not tell. The lantern test was valiant but crude, and no more decisive than a child clapping hands in the dark to measure echoes. Still, Galileo's failure contained a quiet triumph. For the first time, someone had attempted to time light itself, to bring the mystery into the realm of experiment. It was not philosophy, nor geometry, nor speculation about divine perfection. It was a practical scheme, one that could in principle succeed if only the instruments were sensitive enough. The question of whether light had a finite speed had now crossed a threshold. It was no longer the province of metaphysics alone. It had become a scientific problem, waiting for a new kind of evidence. As the 17th century opened, the world was on the brink of revolutions in mathematics, astronomy, and natural philosophy. Telescopes were probing the skies, clocks were growing more precise, and a restless spirit was spreading through Europe. In such an age, the ancient assumption that light was instantaneous would not survive unchallenged. The illusion of emptiness, of a universe where brightness filled space without travel, was about to give way. The stage was prepared for a Dane who would look not across valleys on Earth, but across millions of kilometers in space, reading the heavens like a clock and finding in their ticking the first measure of light's finite speed. The valley experiment of Galileo lingered in memory long after his passing. It showed clearly that light was too fast for human reflexes and too swift for the distances available on Earth to reveal its true pace. The question was not settled, but it was sharpened. Light might yet be finite, though its speed must be extraordinary. Philosophers and natural scientists returned to the problem again and again, turning it over like a puzzle box, finding no way to open it. The old conviction of instantaneity persisted, reinforced by the fact that in every ordinary experience, light seemed immediate. When a cannon fired across a field, the flash was seen at once, while the sound lagged. When a star appeared at dusk, it was as if its light were already present, never delayed, already waiting for the eye. And yet some thinkers began to feel the unease of contradiction. If sound took time to move through air, Why should light not also take time, even if far swifter? If a stone thrown through water required a moment to reach its mark, why should the shining of light not also consume an interval as it crossed space? The more the new science of motion developed, the more suspicious it seemed that light alone should belong to the realm of the infinite. The Renaissance had taught that nature could be measured, that all things might be put to the test. The infinite was no longer a satisfying answer. Galileo's students and successors carried his spirit of experiment forward, though few dared attempt the lantern test again. Instead, they pondered new ways. Could a prism, splitting white light into colors, reveal a delay between hues? Could the eclipses of stars or the phases of the moon provide a natural clock? Some argued that the heavens might contain the answer, for the vastness of cosmic distances might stretch light's flight into a measurable time. But these remained hopes rather than results. No terrestrial experiment could yet capture light in flight. The philosophical weight of the problem was heavy. Descartes had insisted that the cosmos was filled with an ether that transmitted changes instantly. Newton, soon to arrive on the stage, would argue for light as a stream of corpuscles, tiny particles launched from luminous bodies. If such corpuscles moved, might they not have speed? But if they were weightless, perhaps they leapt across space in an instant. Even the greatest minds could not agree. Each system of natural philosophy carried its own assumptions about light's velocity, and none possessed the means to prove it. The 17th century was becoming an age of measurement. Pendulum clocks were keeping time with unprecedented accuracy. Telescopes were resolving moons around distant planets. Mathematicians were inventing calculus to describe change and motion in precise terms. In such a climate, the question of light's speed could not remain an idle speculation. It cried out for an answer as clear and numerical as the fall of an apple or the swing of a pendulum. Yet, as the century wore on, the Earth seemed too small a stage. Distances of hills and valleys were trivial compared to the suspected swiftness of light. Even the fastest horse could not give chase, nor could the finest stopwatch capture the instant of arrival. Human senses were outmatched. What was needed was a clock larger than any machine, a distance greater than any valley, a signal stronger than any lantern. The search for the speed of light would turn away from Earth altogether and look instead to the skies. The moons of Jupiter moved like celestial timekeepers, eclipsing in and out of shadow with steady rhythm. To watch them was to watch a cosmic clock, its hands sweeping across hours and days with perfect regularity. Here lay the chance that had eluded Galileo. Across the gulf of space, light traveled for minutes and perhaps for hours before reaching Earth. If its speed were finite, if it did indeed take time to cross, then the ticking of Jupiter's moons might betray the delay. The heavens themselves would become the laboratory, and their precision would succeed where lanterns had failed. Thus, the story of light moved from valleys and hilltops to the vast theatre of the solar system. Galileo's frustration had revealed the need for greater scales, and nature was ready to provide them. The illusion of instantaneity, so ancient and so persuasive, was about to be broken. A Danish astronomer would take the stage, reading the late arrivals of eclipses not as errors, but as messages carried across space, proving for the first time that light indeed had a speed. The age of speculation was ending, and the age of measurement was beginning. The sky of the 17th century was filled with new revelations. Telescopes had shown that the moon was scarred with mountains and valleys, that Saturn carried strange rings, and that Jupiter possessed a family of moons dancing around it, in miniature imitation of the solar system itself. To astronomers, the moons of Jupiter were not merely curiosities, they were natural timekeepers. Each moon fell into eclipse as it passed into Jupiter's shadow and emerged again with a punctuality that rivaled the best clocks on Earth. For navigators seeking longitude, these eclipses were a promising aid. for by recording the moment of a moon's disappearance or reappearance, one could fix the position of the Earth relative to Jupiter. The heavens, it seemed, offered a celestial chronometer. Among the young astronomers drawn into this grand project was a Dane named Ole Rømer. Born in Copenhagen in the year 1644, he grew up in a Europe bursting with new science. Galileo had been condemned but not forgotten. Kepler's laws of planetary motion were widely known, and Descartes' philosophy filled libraries with its bold visions. Rømer's talent for mathematics and observation earned him a place in the circle of the great French astronomer Jean Picard, who was then engaged in refining maps and celestial tables. Through Picard, Rømer gained access to the Paris Observatory, at that time the most advanced astronomical establishment in the world. It was here in Paris that Rømer turned his attention to the eclipses of Io, the innermost of Jupiter's large moons. Io slipped behind Jupiter every 42.5 hours with mechanical regularity. Astronomers timed these events carefully, recording the moment when the moon vanished and reappeared. Over weeks and months, one could build up a schedule of eclipses as dependable as the ticking of a clock. Yet the data contained a puzzle. Sometimes Io seemed late, sometimes early, as much as 10 or 15 minutes out of step with prediction. Were the tables wrong, or was something stranger occurring? Most astronomers suspected that the irregularities came from imperfections in observation. Telescopes varied in quality, clouds interfered, and the human eye was easily deceived. But Rømer began to suspect a deeper cause. He noticed that the apparent lateness of Io's eclipse correlated with the Earth's motion around the Sun. When the Earth was moving away from Jupiter, the eclipses came later than expected. When the Earth moved closer, they arrived earlier. It was as though the signal itself, the light carrying the image of Io's disappearance, was delayed or advanced by the changing distance between the two planets. This was a daring thought. It meant that light did not arrive instantaneously, but took time to cross space. The difference of 10 or 15 minutes could be explained if light required that much extra time to travel across the additional span of Earth's orbit. In the year 1676, Rømer made the bold announcement. He declared that light had a finite speed, and by his calculations, it crossed the diameter of Earth's orbit in about 22 minutes. Converting this into a velocity, he gave a value of roughly 220,000 kilometers per second. The result was astonishing. For the first time in history, the speed of light had been measured, not in vague terms of infinity or immediacy, but in concrete numbers. The value was lower than the modern figure of 299,792 kilometers per second. Yet it was of the same order of magnitude, a remarkable achievement given the tools of the time. Rømer had looked to the skies and found in the tardiness of a moon the secret of light's flight. Not everyone accepted his conclusion. Some argued that Jupiter's moons might be perturbed by hidden forces, or that errors in telescopes were to blame. Others, committed to the Cartesian doctrine of instantaneous light, resisted the idea outright. Even Isaac Newton, though impressed, treated the value cautiously. But the evidence spoke for itself. Observers in Paris recorded that the eclipse of Io on the 9th of November 1676 occurred 10 minutes later than predicted, precisely as Rømer had forecast. It was proof by anticipation, a scientific triumph. This moment was revolutionary. For the first time, humanity had numbers for the speed of light, numbers that transformed it from metaphysical speculation into measurable reality. Light was no longer infinite, no longer exempt from the laws of motion. It was a traveler, swift beyond all earthly things, but still finite. The illusion of instantaneity, carried from Aristotle to Galileo, was broken. The universe had yielded one of its most guarded secrets. and the consequences would ripple outward into every branch of physics and astronomy. Yet Römer's measurement, brilliant as it was, left room for refinement. The observational difficulties were great, and the accuracy was limited. A value of 220,000 kilometers per second was remarkable, but it was not precise enough to satisfy later generations. The seed had been planted, but others would need to water it to improve the method and to confirm the truth by independent means. The torch of discovery was lit, and in the coming century, it would pass to another astronomer who, while searching for one phenomenon, would stumble upon another, giving the second great proof that light moved with finite speed. The heavens had spoken through Jupiter's moon, but the story was not yet complete. A few decades later, James Bradley, while hunting for the elusive shift of stellar parallax, would find in the stars themselves a new confirmation of Römer's insight, a geometric tilting that revealed once more the swiftness and the finitude of light. The quest had moved beyond valleys and lanterns, beyond even the moons of Jupiter. It was now written across the vault of the sky itself. Römer's announcement in Paris reverberated through the world of science like a tremor. The declaration that light possessed a finite speed challenged the convictions of philosophers and natural scientists alike. In the Great Hall of the French Academy of Sciences, he presented his findings, calmly laying out the delays of Io's eclipses, the correlation with the Earth's orbital position, and the inevitability of the conclusion. Those present were stunned. For centuries, light had been treated as instantaneous, as pure presence, as a medium of divine perfection. To hear that it was bound by speed, that it required measurable time to cross the cosmos, felt almost heretical. The debate that followed was fierce. Followers of Descartes, whose influence still dominated French thought, were reluctant to abandon the doctrine of instant transmission. To admit that light had finite speed was to confess that Descartes' cosmic machinery was incomplete. Some whispered that Römer's data were mistaken, that the telescopes misled, or that the orbit of Io was not as regular as assumed. Others argued that Jupiter itself might slow its moons, that unseen forces could explain the apparent delay. But Römer remained steadfast. The consistency of the pattern, its alignment with the Earth's changing distance, left no room for doubt. Jean Picard and Giovanni Domenico Cassini, both distinguished astronomers of the observatory, lent cautious support. Cassini had initially noticed irregularities in the eclipses years earlier, but had hesitated to propose so bold an explanation. Römer, younger and less bound by tradition, carried the idea to its full conclusion. By daring to suggest that light took 22 minutes to cross the diameter of Earth's orbit, he stepped beyond speculation into the realm of quantitative science. The prediction that Io's eclipse on the 9th of November 1676 would occur 10 minutes late proved decisive. When the delay was observed, skeptics could no longer dismiss the idea as fantasy. The universe itself had provided the experiment. Unlike Galileo's lanterns, which were defeated by the brevity of terrestrial distances, Römer's laboratory was the solar system. The path of Earth around the Sun, nearly 300 million kilometers across, stretched light's journey long enough to expose its finite nature. Still, the precision of his measurement was limited. The exact scale of the solar system was not yet fully known. Astronomers could estimate Earth's orbital diameter, but uncertainties remained. Thus, Römer's value of roughly 220,000 kilometers per second was only approximate, but it was revolutionary nonetheless. Even if not exact, it was the first number ever attached to the speed of light. It was proof that the question had an answer, and that the answer could be found in nature. The significance of Römer's work extended far beyond optics. If light had speed, then the universe had a clockwork more subtle than previously imagined. Astronomers could now understand delays in eclipses, corrections in celestial navigation, and even the timing of events across space. For sailors attempting to fix their longitude on the high seas, the reliability of Jupiter's moons as a cosmic timepiece was shaken. But the new understanding of light opened pathways to deeper comprehension of celestial mechanics. Newton, in England, followed the reports with keen interest. His own theory of light as particles could accommodate a finite speed more easily than Descartes' instantaneous wave. In his Principia, published in 1687, Newton referenced the idea that light moved in time, though he left the details to astronomers. Rømer's discovery thus wove itself into the foundations of modern physics, influencing the great systems that would dominate the century. Across Europe, scholars debated the implications. Some insisted that the soul of vision could not be bound by speed, that to see was to touch the world without delay. Others embraced the new picture, marveling at the thought that light, for all its swiftness, was still finite, still a traveler in the vastness of space. In taverns and universities, the news was retold with awe. A moon, invisible to the naked eye, had betrayed the secret of the heavens. Rømer himself returned to Denmark, where he continued to work on astronomy and navigation. Though his later years were devoted to practical matters, such as the improvement of street lighting in Copenhagen, his name was forever linked to the great revelation of light's velocity. He had transformed a philosophical question into an empirical fact. The cosmos was no longer instantaneous. It breathed with rhythm, and even the flash of light required time to reach the eye. The debates of the era slowly subsided. The evidence grew as more observations confirmed the delays. Though some philosophers clung to the old doctrines, the scientific community could not ignore the weight of prediction and verification. The finite speed of light became accepted, even if its exact value remained uncertain. The foundation had been laid for future measurements, more refined and more precise, that would pin down the number with increasing accuracy. Yet there was still a lingering sense of incompleteness. Rømer had shown that light was finite, but the question of its exact velocity remained open. Could one trust a value derived from such vast distances and uncertain scales? Could there be another way, more direct, to measure the swiftness of light? It was into this atmosphere that James Bradley would step a few decades later, armed with patience and geometry, ready to search the heavens for stellar parallax, but destined instead to find something even more profound: the aberration of starlight, a subtle tilting that offered new confirmation of Rømer's daring claim. The aftermath of Rømer's bold claim rippled outward through Europe for decades. His demonstration was more than a technical note in astronomy. It was a turning point in how natural philosophers thought about the universe. The conviction that light was instantaneous had been carried forward from antiquity, reinforced by common experience and sanctified by the great systems of Aristotle and Descartes. To say that light was finite was to say that even the purest phenomenon in nature obeyed limits, that it too was bound by measure and by number. For navigation, the revelation brought both difficulty and insight. Mariners had hoped to use the eclipses of Jupiter's moons as a universal clock for determining longitude at sea. By timing an eclipse precisely and comparing it with tables, one could find the difference between local time and the time at a fixed meridian, thereby finding position. But Rømer's discovery showed that the eclipses were not perfectly punctual. They arrived early or late, depending on the Earth's position in its orbit, shifted by the finite flight of light. The moons could still be used, but the correction had to be applied. A subtle delay in the heavens had to be accounted for by those who wished to cross oceans. The cosmos had revealed both its utility and its complexity. Philosophers grappled with the meaning. If light required 22 minutes to cross the orbit of Earth, then light from the sun itself took about 8 minutes to reach us. The sun we see is not the sun of the present moment, but of the recent past. The stars overhead are not present at all, but delayed by years, decades, and even centuries. the universe becomes a museum of the past, each ray of light a message sent long ago, traveling tirelessly until it arrives at the eye. This idea unsettled many, for it suggested that the heavens were not an eternal instant, but a stream of delayed signals, forever out of step with now. Despite resistance, the logic proved irresistible. The prediction of lateness, confirmed by observation, was an argument of a new kind, one that philosophers could not dismiss. The age of speculative reasoning was giving way to the age of empirical proof. In the salons of Paris and the halls of London, in the observatories of Rome and Copenhagen, the finite speed of light became an accepted truth. The exact number remained debated, but the principle was firm. Rømer himself continued to serve his country with distinction. Back in Copenhagen, he worked on improving instruments, building waterworks, and even organizing civic affairs. He never again reached the dramatic heights of his Parisian revelation, but his legacy was secure. He had opened a new path in science. Others would refine the measurement, correct the value, and develop new methods, but all would walk in his footsteps. The philosophical consequences were immense. Once light was known to be finite, it could be treated like any other physical phenomenon. It became part of the framework of mechanics and astronomy. It became possible to imagine delays, to calculate travel times, to conceive of a universe not bound by perfection, but by laws of motion. The dream of infinite immediacy had ended. In its place stood a universe governed by measure, a cosmos where even light had to run a race across space. Yet the story did not end in 1676. The number Rømer gave was too small, burdened by the uncertainties of planetary distances. More precise work would be needed, and a new generation of astronomers was already looking to the stars with refined instruments, searching not only for parallax, the hoped-for evidence of Earth's motion, but also for any subtle displacement that might betray new truths. In this search, James Bradley would stumble upon a phenomenon never before imagined, one that would confirm Rømer's bold claim in an entirely different way. The light of the stars would not arrive where expected. It would be tilted by the Earth's motion, forming an aberration that revealed not only the planet's speed, but also the speed of light itself. The moons of Jupiter had opened the first door, but the starlight itself would soon stride through the second. Humanity had taken its first true measurement of the swiftness of light. Now it was ready to take the next. The early 18th century was an age of relentless curiosity. Telescopes were steadily improving, their lenses polished with greater care, their mounts steadier, their clocks more precise. Astronomers across Europe were driven by a singular quest, to prove once and for all that the Earth moved around the Sun. The Copernican model, reinforced by Kepler's laws and Newton's gravitation, was widely accepted by the learned, but direct observational proof remained elusive. The key was stellar parallax. If the Earth truly orbited the Sun, then the stars should appear to shift slightly against the background of more distant stars as the planet moved from one side of its orbit to the other. The effect would be tiny, but in principle, it must exist. Among those who sought this elusive sign was James Bradley, an English clergyman turned astronomer, meticulous and determined. He was born in Gloucestershire in 1693 and educated at Oxford, where he quickly earned a reputation for his skill in observation. Encouraged by his uncle, the respected astronomer James Pound, Bradley pursued the problem of parallax with great dedication. He gained access to fine instruments and soon became known among London's scientific circles. In the year 1725, he and his friend Samuel Molyneux constructed a large zenith sector, a telescope fixed to measure the precise positions of stars passing overhead. With this, they set out to capture the subtle shift that would at last confirm Earth's orbital motion. Their attention fell on Gamma Draconis, a bright star nearly overhead from London. Night after night, they measured its position with exquisite care. If parallax existed, then over the course of 6 months, the star should drift first one way and then the other, following the Earth as it moved around the Sun. The displacement was expected to be only a few arcseconds, smaller than the width of a coin seen from several kilometers away, but within reach of their instruments. For months they labored, recording angles, refining measurements, watching the star with unwavering patience. What they found, however, was not what they expected. The star did shift, but not in the predicted pattern. Instead of moving back and forth along a line, Gamma Draconis traced a small ellipse in the sky, completing a full cycle over the course of a year. The amplitude of this motion was about 20 arcseconds, much larger than the anticipated parallax. At first, Bradley was puzzled, even disappointed. The signature of parallax, the direct proof of heliocentrism, still eluded him. Yet the pattern was too regular, too exact to be dismissed as error. Something else was at work. Bradley considered every possibility. Could the telescope itself be shifting? Could refraction in the atmosphere bend the starlight? Could the Earth's axis be wobbling? None of these explanations matched the observed pattern. Then one day, while sailing on the Thames, Bradley noticed how a flag atop the mast streamed not in the direction of the wind itself, but at an angle determined by the motion of the boat. A thought struck him. Perhaps the starlight behaved the same way. If the Earth were moving swiftly through space, then the light of a star entering a telescope would be tilted, just as raindrops seem to slant against a moving carriage. The telescope must be slightly inclined to catch the starlight, and as the Earth's direction changed throughout the year, the required tilt would also change, tracing out an annual ellipse. This was the phenomenon Bradley had discovered: stellar aberration. It was not parallax, but it was something even more profound. It showed that starlight arrived at Earth at a finite speed, and that the Earth's orbital motion altered its apparent direction. The angle of aberration depended directly on the ratio between Earth's velocity and the speed of light. Measuring the one gave a measure of the other. The Earth's orbital speed was known from Kepler's laws and Newton's theory of gravitation, about 30 kilometers per second. The angle of aberration measured by Bradley was about 20 arcseconds. From this ratio, he deduced that the speed of light must be about 10,000 times greater than the Earth's orbital speed, giving a value of approximately 300,000 kilometers per second. This result was strikingly close to the modern figure. Bradley's method, though indirect, provided a confirmation of Romer's insight with far greater precision. The beauty of stellar aberration lay in its universality. Unlike Romer's observation, which relied on the peculiarities of Jupiter's moons, Bradley's discovery applied to every star in the sky. Any beam of light arriving at a moving Earth would exhibit the same effect. It was a geometric inevitability, a cosmic signature written across the heavens. No philosopher could argue that it was illusion or accident. The aberration was as real as the seasons, a direct consequence of motion and finite speed. When Bradley presented his findings to the Royal Society in 1729, the impact was immediate. Here was confirmation not only of Romer's daring claim, but also of the Copernican system itself. The Earth's motion was no longer a matter of belief or inference. It was inscribed in the apparent tilt of every star. The universe had provided a second proof that light was not instantaneous. It moved with finite, measurable velocity, and the geometry of the Earth's orbit revealed it. Yet Bradley himself was cautious. He refrained from boasting about having measured the speed of light. He presented his work as a careful description of a new phenomenon, leaving others to appreciate the deeper implications. His modesty did not diminish the magnitude of his discovery. In truth, he had given science not only a more accurate value for the speed of light, but also a new tool for understanding the dynamics of the Earth's motion. The aberration of starlight became one of the great triumphs of 18th century astronomy. It proved that the Copernican model was correct beyond doubt, it confirmed Romer's insight, and it brought the speed of light into sharper focus. For the first time, astronomers could be confident that light moved at about 300,000 kilometers per second, an extraordinary swiftness, but still finite. The implications for physics, navigation, and cosmology were immense, and yet, as precise as Bradley's result was, it remained indirect. Light speed had been inferred from geometry and celestial mechanics, not from a controlled experiment on Earth. The heavens had provided two great proofs, Romer's and Bradley's, but the yearning for a direct terrestrial measurement persisted. Could human hands, using instruments alone, capture the flight of light across a measurable distance? That challenge would await the 19th century, when Arago, Fizeau, and Foucault would bring the laboratory into the story and measure the swiftness of light not by the tardiness of moons or the tilt of stars, but by the ticking of machines built on Earth. Bradley's work did not end with a single announcement. For years he pursued the effect, refining his observations, watching not just Gamma Draconis, but other stars in different regions of the sky. Each one confirmed the same pattern. Each one showed the small annual ellipse, the telltale signature of aberration. The consistency of the phenomenon left no doubt. It was not an accident of one star, nor a quirk of one telescope. It was a law written in the very act of light's arrival to a moving Earth. The Royal Society listened with rapt attention when Bradley presented his findings. They understood immediately the depth of what he had uncovered. The elusive parallax was still missing, but in its place stood something arguably greater. Here was a phenomenon that proved not only Earth's motion, but also the finite speed of light, all in one stroke. The fellows marveled at the ingenuity of his interpretation. Where others might have dismissed the anomaly as error, Bradley had seen in it a hidden pattern, like a code to be deciphered. He had taken disappointment and turned it into triumph. News spread across Europe, carried by letters and journals. Astronomers in France, Germany, and Italy tested the result against their own observations. Everywhere the aberration appeared, small but undeniable, it quickly became one of the pillars of 18th century astronomy. Copernicus had set the planets in motion, Kepler had written their laws, Newton had described the force that bound them, and Bradley had revealed the subtle optical proof that the Earth truly circled the Sun. No longer could skeptics claim that heliocentrism was a convenient fiction. The stars themselves leaned before the rushing Earth, tilted as though acknowledging the planet's speed. The value for the speed of light that emerged from Bradley's measurements was astonishingly close to the modern figure. He deduced a velocity of about 300,000 kilometers per second, barely a few percent away from the accepted value today. To think that such precision could be achieved with a wooden telescope mounted in a London home, guided only by careful eyes and patient recording, is a testament to both his skill and the power of geometry. It showed that the cosmos could reveal its deepest secrets not through grand experiments, but through quiet persistence and clear thought. The philosophical consequences were as striking as the scientific. If light had finite speed, then vision itself was a kind of time travel. To look at the moon was to see it 1 second in the past. To look at the sun was to see it 8 minutes in the past. To gaze at the stars was to peer centuries backward. The heavens were not present, but delayed. Every night, sky was a record of history, a library of ancient light. For theologians and philosophers, this was a dizzying thought. For scientists, it was a revelation, for it meant that light could serve as a probe of both distance and time. Bradley himself remained modest. He spoke carefully of what he had found, never exaggerating, always cautious. He did not trumpet his achievement as a conquest, though it was one of the greatest of his age. His temperament was that of a patient observer, not a bold showman. This humility may have helped the acceptance of his discovery, for it was presented not as a challenge to tradition, but as a simple fact of observation. The aberration was there, it could be seen, measured, and predicted. No philosophy could erase it. Over time, the effect became a tool for practical astronomy. By correcting for aberration, astronomers could refine their star catalogues and improve navigation. The tilt of starlight was no longer an obstacle, but a predictable adjustment, one more factor in the precise mapping of the heavens. What had begun as a puzzle became an instrument of accuracy. In this way, Bradley's discovery passed quietly into the fabric of science, accepted so thoroughly that it became almost invisible, a background assumption of every star chart. The broader cultural world absorbed the news as well. Writers and thinkers marveled at the idea that the stars bent their positions in sympathy with Earth's race around the sun. The metaphor of slanting rain or wind against a moving ship entered common explanation. The phenomenon was easy to imagine, even for those who could not follow the geometry. One had only to think of running in a storm, the rain striking the face at an angle no matter how it fell. The universe, it seemed, behaved in the same way, with Earth forever rushing through a storm of starlight. Yet for all its success, the discovery left questions unanswered. Could the speed of light be measured more directly, not inferred from cosmic geometry, but captured in a terrestrial experiment? Could human instruments be made fast enough, precise enough, to watch light itself cross a distance on Earth? The dream of such a measurement stirred in the minds of physicists. Bradley had confirmed the finite speed, and he had pinned down its value with impressive accuracy, but the yearning for a laboratory proof remained. That challenge would fall to the 19th century, when ingenious machines of wheels and mirrors would seize the elusive swiftness of light on earthly scales. Bradley's patient discovery did more than confirm the finite speed of light. It reshaped astronomy itself. Once stellar aberration was accepted, every star's apparent position had to be corrected. Catalogues of the heavens, those great maps by which sailors steered and astronomers charted the sky, were all subject to this subtle tilt. Without correction, the placement of stars would wander in annual ellipses. With correction, their true positions could be fixed. In this way, Bradley's work became indispensable, a quiet revolution that transformed precision astronomy from guesswork into measured certainty. The phenomenon also gave new confidence in the Copernican model. For more than a century, the heliocentric system had rested on the elegance of Kepler's laws and the force of Newton's gravitation. But to skeptics, it still seemed lacking in direct proof. Parallax, the gold standard of confirmation, remained invisible with the instruments of the time. Aberration, however, was inescapable. Its pattern matched exactly what must be expected if the Earth orbited the Sun. It was, in effect, a surrogate proof, a cosmic signal that could not be explained away by geocentric schemes. The Earth's motion was written in the sky, not as a grand shift, but as a delicate lean of light. Philosophers, poets, and natural scientists alike seized upon the implications. If the stars leaned before the Earth's rushing course, then humanity was not at the center, but in motion, adrift in the vast sea of space. The heavens were not fixed, not immutable, but dynamic and relative. The very act of seeing was altered by the planet's speed. To some, this was humbling, to others, exhilarating. It showed that human senses were not absolute, but shaped by the grand motions of the cosmos. Even the direction of a star depended on Earth's flight. The numerical value of the speed of light derived from aberration was astonishing in its precision. Around 300,000 kilometers per second, far beyond any earthly velocity, yet finite. It confirmed Romer's earlier estimate and corrected it. The delay of Jupiter's moon had hinted at light's swiftness, but Bradley's geometry nailed it down. For the first time, science possessed two independent methods, astronomical yet distinct, both converging on the same truth. Light was not infinite. It had a speed, vast but measurable, and now two lines of evidence agreed upon it. Still, the manner of measurement remained indirect. No experiment had yet caught light racing across a measured distance on Earth. Galileo's lanterns had been too crude. Romer had relied on the moons of Jupiter. Bradley had leaned on geometry and the Earth's motion. Each step was ingenious, yet none brought the satisfaction of watching light itself cross a known space in real time. That desire lingered, a challenge to the ingenuity of future generations. Meanwhile, Bradley's career advanced. He was appointed Astronomer Royal in 1742, a post he held until his death. From Greenwich, he supervised observations, refined instruments, and improved the accuracy of the National Star Catalogue. His name became synonymous with precision, yet he remained the same cautious man, never exaggerating his achievements, always careful to distinguish observation from speculation. To those who knew him, he was modest to the point of reticence, a man who let his data speak louder than his voice. His legacy endured. Aberration became a standard correction in astronomy, as familiar to observers as atmospheric refraction or precession. His careful methods inspired later generations to pursue ever greater accuracy. And his discovery stood as a reminder that science often advances not by achieving the expected, but by recognizing the unexpected. Bradley had sought parallax and found instead a new phenomenon, one that proved more powerful than the one he had missed. In failing to achieve one goal, he had succeeded in reshaping astronomy. By the close of the 18th century, the finite speed of light was beyond dispute. It was a number to be used, corrected for, applied in calculation. Yet the hunger for a direct terrestrial measure had only grown stronger. The 19th century was dawning, an era of machines, of refined optics, of rotating mirrors and toothed wheels. Arago would attempt the first terrestrial tests, and soon after, Fizeau and Foucault would succeed where Galileo had failed, catching light itself in flight on Earth. The age of astronomy had provided the insight, but the age of the laboratory was about to seize the prize of precision. The 18th century had closed with the finite speed of light firmly established. Romer had seen its delay in the moons of Jupiter. Bradley had confirmed it in the tilt of starlight. Together, they had shown beyond question that light was a traveler, not an instantaneous presence. Yet both methods were indirect, dependent on the vast clockwork of the solar system. No experiment had yet taken place on Earth that could seize light's motion within human reach. For centuries, philosophers had dreamed of measuring the flight of light across a terrestrial distance. But until the 19th century, the dream had always slipped away. Now, in an age of growing precision, with better optics and faster machinery, that dream began to take form. It was Dominique François Arago who first attempted to bridge the gap. Born in 1786, Arago rose to prominence as a brilliant French physicist and politician, a man equally at home in the Chamber of Deputies and the Observatory Dome. His mind was restless and inventive. In the early 1800s, he turned his attention to the possibility of measuring light on Earth. He devised experiments with prisms, attempting to detect whether light's speed might differ when passing through glass compared to air. His aim was not only to catch light in motion, but to test rival theories of its nature. Newton had described light as corpuscles, tiny particles emitted from luminous bodies, while Christian Huygens had championed the wave theory, If light moved more slowly in dense media, as Huygens predicted, then a careful prism experiment might reveal the difference. Arago's instruments were not yet equal to the task. The deviation he sought was too slight, the sensitivity of his apparatus too crude. The experiment ended in frustration, the sought-for variation invisible. Yet his effort was not in vain. By daring to attempt a terrestrial measure, he set the stage for those who followed. He showed that the question could be asked in the laboratory, not only in the heavens. The problem was now clearly defined. Devise a way to send light across a measurable distance on Earth and to time its passage with instruments rather than with the clockwork of planets. The challenge was formidable. Light was unimaginably fast, so fast that across ordinary distances, the travel time was less than a fraction of a millionth of a second. To capture such swiftness, one needed either extraordinary timing or an ingenious method of multiplying the effect. The solution would come from Hippolyte Fizeau, a young French physicist with a gift for experimental design. In 1849, at the age of only 29, Fizeau conceived a method that finally brought the velocity of light within terrestrial grasp. He arranged a brilliant beam of light to pass through the gaps of a rapidly rotating toothed wheel, travel across several kilometers of open air, reflect from a mirror, and return through the same wheel. When the wheel rotated slowly, the returning light passed back through the original gap, and the observer saw a bright flash. But as the wheel spun faster, the returning light struck the edge of the next tooth and was blocked. By adjusting the speed of the wheel until the returning light vanished, Fizeau had in effect measured the time required for light to travel to the distant mirror and back. The geometry of the wheel, the distance to the mirror, and the rotation rate combined to yield the speed of light. The result was breathtaking. Fizeau reported a value of about 313,000 kilometers per second, astonishingly close to the modern figure. For the first time, the swiftness of light had been caught on Earth, measured by human instruments, not merely inferred from the heavens. It was a triumph of ingenuity, a moment when centuries of speculation gave way to the certainty of experiment. The wheel and mirror had succeeded where lanterns and prisms had failed. The scientific world received the news with admiration. Here at last was a terrestrial measurement, a proof that human machines could reach into the domain of the nearly instantaneous. Fizeau's method was not perfect. The precision was limited, and small errors in distance or rotation speed could shift the result. But the principle was sound, and the number was strikingly accurate. It marked the beginning of a new era, when the speed of light would no longer be the province of astronomers alone, but also of experimental physicists. Within a year, François Foucault, another inventive French physicist, introduced an improvement. He replaced the toothed wheel with a rotating mirror. In Foucault's apparatus, a beam of light struck the spinning mirror, reflected to a distant mirror, and returned. During the light's journey, the spinning mirror had turned slightly, so the returning beam was deflected by a small angle. By measuring this angle and knowing the speed of rotation, Foucault could calculate the travel time of the light, and hence its velocity. His method allowed for shorter distances and greater precision than Fizeau's wheel. In 1850, Foucault reported his results, giving a value slightly lower than Fizeau's, about 298,000 kilometers per second. More importantly, his experiment showed that light traveled more slowly in water than in air, a finding that struck a decisive blow against Newton's corpuscular theory and in favor of the wave model. The debate that had divided physicists for more than a century was resolved by a single rotating mirror. Light was a wave, and its finite speed could be measured on Earth with accuracy. By the middle of the 19th century, the speed of light was known to within a few percent. What had once been the subject of myth and speculation was now a number to be written in tables and used in calculation. The success of Fizeau and Foucault demonstrated the power of precision experiment. With clever devices and patient measurement, even the most elusive of phenomena could be captured. the story of light had moved from philosophy to astronomy to laboratory, each step bringing greater clarity. The implications were profound. If light had a finite and measurable speed, then time and space were woven together in new ways. Distances could be translated into times, times into distances. Astronomers could correct for delays, physicists could test theories of waves, and engineers could dream of harnessing light in technology. The number itself, near 300,000 kilometers per second, became a constant of nature, a reference point against which other measurements were judged. And yet, even as the triumphs of Fizeau and Foucault were celebrated, one man would push the pursuit further still. An American physicist named Albert Michelson would devote his life to measuring the speed of light with ever greater precision. His refinements would reduce uncertainties to fractions of a percent. His experiments would probe the nature of space itself, and his name would become inseparable from the constant sea. The 19th century had begun with the first successful terrestrial measurements. It would end with a level of precision that rivaled anything possible even in modern times. Fizeau's wheel had shown the way, but to appreciate its achievement, one must imagine the delicacy of the setup. A bright source of light, in his case, the concentrated glow of a lamp, was aimed through the spaces of a carefully cut wheel. Each gap was no wider than the thickness of a finger, and the wheel spun with thousands of revolutions each minute. Beyond it, several kilometers away, a mirror had been stationed, polished to reflect the beam back with perfect steadiness. The light traversed the distance, touched the mirror, and returned in barely a fraction of a second. To the eye at the original apparatus, the beams seemed steady at first, but as the speed of the wheel increased, the flashes vanished, swallowed by the teeth. It was a kind of optical heartbeat, extinguished not by distance, but by speed itself. By timing the rotation at which the flashes disappeared, Fizeau found a way to pin down the impossible. He calculated that light crossed each kilometer in less than 3/millionths of a second. Multiplying by the distance to the mirror and back, the number emerged, over 300,000 kilometers every second. To put it in perspective, a cannonball might fly 1 kilometer in a second, but light in the same instant would circle the Earth 7 times. It was a staggering speed, so immense that it bordered on the unimaginable. Yet here it was, recorded by the clicking of a wheel, written in human numbers. The effect on the scientific community was immediate. The achievement was celebrated as a decisive victory for experimental physics. For centuries, the question had lingered in the realm of astronomy and philosophy. But now, it had been brought home, caught in a laboratory, witnessed by instruments and human eyes. The speed of light was no longer a distant inference, but a direct measurement. Still, the wheel was only the beginning. The method was ingenious, but its reliance on long distances and rapid mechanical rotation limited its precision. Small uncertainties in the exact separation of the mirrors or the stability of the wheel introduced errors. The accuracy was remarkable for its time, but the hunger for refinement was insatiable. Scientists wished to know not only that light moved at 300,000 kilometers per second, but whether it was 310 or 315, whether the number could be fixed to a single place of decimals. The dream of exactitude, so characteristic of the 19th century, demanded something more. François Foucault provided it. His improvement, though simple in concept, was revolutionary in practice. By using a rotating mirror instead of a wheel, he transformed the measurement from an on-off flicker into a deflection that could be read with precision. Light from a source struck the spinning mirror, traveled to a distant reflector, and returned. In the interval, the mirror had turned slightly, so the returning beam was displaced. By measuring the angle of that displacement and knowing the speed of rotation, Foucault could calculate the time of flight. the advantage was profound. Shorter distances sufficed. The apparatus could be contained within a laboratory, and the results were more exact. In 1850, Foucault announced his findings. He gave a value near 298,000 kilometers per second, closer than Fizeau's, and in line with what would later be confirmed. More than that, he repeated the test with light traveling through water. If Newton's corpuscles were real, they ought to accelerate in denser media, but if Huygens' waves were real, they ought to slow. Foucault's result was unambiguous. Light moved more slowly in water than in air. The wave theory triumphed, and the particle model that had held sway since Newton's time was cast aside. In a single experiment, Foucault had both measured the swiftness of light and resolved a century-long debate. The consequences were far-reaching. The wave theory of light, now vindicated, provided the foundation upon which James Clerk Maxwell would soon build his electromagnetic theory. The idea that light was an electromagnetic wave traveling at a fixed velocity would have been unthinkable without Fizeau's and Foucault's groundwork. Their machines, humble in appearance, had opened the path to the grand unification of optics and electricity. Public fascination grew alongside scientific respect. Newspapers described the experiments with excitement, marveling that human beings could catch light itself in flight. The image of a wheel chopping the beam, of a mirror spinning faster than the eye could follow, captured the imagination. It was as though humanity had trapped the very essence of illumination, measured the heartbeat of the cosmos, and translated it into numbers that anyone could recite. By mid-century, the speed of light was known within a few percent. That precision may seem rough compared to later standards, but it represented a leap beyond anything imagined a generation earlier. What had been a philosophical argument for Aristotle, a lantern trick for Galileo, a celestial puzzle for Römer, and a geometric deduction for Bradley had become, through Fizeau and Foucault, a laboratory fact. The progression was dramatic, a story of thought turning into observation, and observation into experiment. And yet, as the 19th century advanced, a new figure would arrive who embodied the pursuit of precision more than any other. Albert Michelson, born in America and trained in the discipline of naval timing, would devote his life to refining Foucault's method until the uncertainty dwindled to a whisper. His career would elevate the measurement of light from a triumph of ingenuity to a cornerstone of physics, and in doing so, he would help usher in the new century of relativity. The legacy of Fizeau and Foucault spread far beyond their immediate numbers. For the first time, humanity had captured light's speed within the walls of a laboratory, bringing the mystery of the cosmos down to Earth. Their experiments were not mere curiosities, but profound demonstrations that ideas once consigned to philosophy could be tested with machines of glass, steel, and precision. The question of light's nature, long debated since Newton and Huygens, had at last been settled by rotating mirrors and careful timing. Light was a wave, and it traveled through air and water at measurable speeds. The cultural atmosphere of mid-19th century Europe was one of awe at what instruments could reveal. The industrial age had transformed daily life with steam engines, railways, and telegraphs, and now the same spirit of ingenuity was being applied to nature's deepest riddles. If light could be measured, then perhaps nothing was beyond the reach of experiment. The ancient conviction of instantaneity, once defended by Aristotle and Descartes, was now permanently broken. Children learned in schools that light raced across the heavens at 300,000 kilometers per second, and philosophers spoke of a universe woven together by speed and distance. For physicists, the importance of precision could not be overstated. The value of 300,000 kilometers per second was close enough for many purposes, but the hunger for refinement was already stirring. If Fizeau and Foucault could come within a few percent, then why not within a fraction of a percent? Could the number be pinned down to the very digits? This pursuit of exactitude was not idle. Theories of waves, of electricity, and of magnetism all demanded reliable constants. Without them, the equations could not stand. The speed of light thus became not merely an astronomical curiosity, but a cornerstone of physics. Maxwell would soon weave electricity and magnetism into a single theory and find that the predicted speed of electromagnetic waves matched the measured speed of light. This was no coincidence, but revelation. It showed that light itself was an electromagnetic phenomenon, a ripple of fields racing through space. Without the careful numbers of Fizeau and Foucault, the identification might have remained a speculation. With them, it became a certainty. The world, however, was not yet finished with the measurement of light. In America, a young naval officer turned physicist named Albert Michelson would take up the challenge. Trained in the discipline of timing and precision, Michelson would devote his life to pushing the accuracy of Foucault's mirror method to ever finer degrees. His instruments would stretch across basements, observatories, and even mountain valleys. His results would reduce uncertainty until the speed of light became one of the most precisely known numbers in science. And in his famous collaboration with Edward Morley, his refinements would not only measure light's speed, but also confront the very nature of space, setting the stage for Einstein's revolution. The 19th century had begun with the first successful Earth-based measurements of light's speed. It ended with a number known to exquisite precision, embedded in theory and poised to redefine the very framework of physics. What had started with Fizeau's wheel and Foucault's mirror had become the bedrock of a new age, the age of precision, where the swiftness of light was no longer a mystery, but a universal constant at the heart of reality. The story of light had already traveled far by the late 19th century. From Galileo's lanterns to Romer's moons, from Bradley's tilted stars to Fizeau's wheel and Foucault's mirror, the swiftness of light had been proven beyond question. But science in this era demanded more than proof. It demanded numbers of ever-increasing precision. Industrial machines were being built with tolerances measured in thousandths. New instruments of physics sought exact values for constants, and entire theories depended on the reliability of measurement. Into this world stepped Albert Abraham Michelson, a man who would devote his life to refining the velocity of light until its value was fixed with an accuracy that astonished his peers and placed him among the greatest experimental physicists of all time. Michelson was born in 1852 in Prussia and brought to America as a child, where his family settled in Nevada and then California. His early life gave little sign of the meticulous craftsman he would become, but when he entered the United States Naval Academy, his talent for optics and timing quickly distinguished him. Naval training emphasized discipline, precision, and above all, measurement. The timing of guns, the sighting of stars for navigation, the calibration of instruments, all of this shaped his mind. He absorbed the lessons of accuracy as a kind of creed, and in the laboratory, he discovered a joy in refining instruments until they yielded perfect numbers. After graduating, Michelson turned his naval training towards science. He became fascinated by Foucault's rotating mirror method for measuring the speed of light. Where Foucault had used a modest setup, Michelson imagined improvements. He designed larger baselines, better mirrors, steadier mounts, and more powerful light sources. His aim was not simply to repeat the measurement, but to push its uncertainty down by orders of magnitude. In 1879, while stationed as an instructor at the Naval Academy, Michelson performed his first great experiment. Using a long baseline across the grounds, he sent light back and forth between carefully aligned mirrors, timing its deflection with exquisite care. His result, about 299,910 kilometers per second, was the most precise value ever obtained to that date. The scientific community was astonished. Here was a young naval officer, barely past his mid-20s, who had measured the speed of light with an accuracy surpassing the laboratories of Europe. His reputation soared. He soon left the Navy to pursue physics full-time, dedicating himself to the perfection of a measurement. Over the next decades, he refined his apparatus, using longer baselines and more stable mirrors, repeating the experiment in Berlin, in Cleveland, in Chicago, and in the deserts of California. Each time he shaved away uncertainties, narrowing the margin until the value of light speed was known within a few kilometers per second. But Michelson's ambitions did not stop there. His passion for precision extended beyond light's velocity to the very structure of space. In the prevailing physics of the 19th century, light was understood as a wave, and every wave required a medium. Sound traveled through air, water waves through the sea, and light through a hypothetical substance known as the luminiferous ether. This ether was thought to permeate all space, invisible and intangible, providing the stage upon which electromagnetic waves rippled. If the Earth moved through this ether, then the speed of light should vary slightly depending on direction, much as a swimmer moves faster with the current than against it. In 1887, Michelson, together with the chemist Edward Morley, designed an experiment to detect this ether drift. They built an interferometer, a device that split a beam of light into two perpendicular paths, reflected them back, and recombined them to form interference fringes. If light traveled at different speeds in different directions through the ether, the fringes would shift as the apparatus was rotated. Michelson and Morley expected to detect a small but measurable displacement, proof of Earth's motion through the ether. The result was one of the most famous null results in history. No matter how they turned the apparatus, no shift appeared. The speed of light remained the same in all directions, indifferent to the supposed ether wind. The outcome was deeply puzzling, shaking the foundations of 19th century physics. The ether, long assumed to be real, had left no trace. The failure to detect it did not yet kill the concept, but it weakened it fatally. The mystery of how light could be a wave without a medium hung over physics like a storm cloud. Michelson, though disappointed, continued his pursuit of measurement. He refined his interferometer, not only for ether drift, but for precision in length standards. His device was so sensitive that it could detect displacement smaller than a fraction of a wavelength of light. With it, he measured the diameter of stars, resolving the disk of Betelgeuse, and contributed to the definition of the meter itself. His name became synonymous with exactitude. In 1907, he was awarded the Nobel Prize in Physics, the first American to receive the honor, recognized for his precision optical instruments and his measurements of the speed of light. By the early 20th century, thanks largely to Michelson's lifelong dedication, the speed of light was known to within a tiny fraction of a percent. The number 299,860 kilometers per second emerged as the accepted standard, remarkably close to the modern exact value. Michelson had accomplished what generations before him could only dream of. He had taken the most elusive of all motions and fixed it with a certainty rivaling any constant in science. Yet the deeper significance of his work extended beyond numbers. The failure to detect ether drift in the Michelson-Morley experiment set the stage for a radical rethinking of space and time. A young patent clerk in Switzerland named Albert Einstein would seize upon this puzzle, proposing that the speed of light was not only finite, but absolute, the same for all observers, regardless of their motion. In doing so, he would dissolve the ether entirely and reshape physics into the strange and beautiful form we now call relativity. The age of precision had reached its peak with Michelson. He had turned the speed of light from a mystery into a number, from a philosophical speculation into a cornerstone of physics. His mirrors and interferometers had measured not only the swiftness of light, but also the structure of the universe itself. The torch now passed to Einstein, who would take the constant c and elevate it from a measured velocity to a fundamental limit of reality, the cosmic speed at which time and space themselves unfold. Michelson's early triumphs had already secured his reputation, but he was not content with a single great experiment. Precision was to him both a profession and a philosophy, a pursuit that never truly ended. After the success of his first measurement in 1879, he devoted decade after decade to refining his apparatus, lengthening baselines, polishing mirrors to unprecedented smoothness, and pushing light itself to confess its swiftness with ever greater fidelity. Each new attempt narrowed the uncertainty until the speed of light became one of the best-known quantities in all of science. In Berlin, he worked with Hermann von Helmholtz, absorbing the rigor of German experimental tradition. In Cleveland and Chicago, he set up elaborate mirror systems across long corridors, timing light's passage across measured paths. His experiments demanded patience and relentless attention to detail. Even the faintest vibration in the floor, the smallest flaw in a mirror, or the tiniest instability in rotation could spoil the measurement. To control these influences, he invented new methods of mounting, damping, and calibration. He was not merely a measurer of light, but a master craftsman of instruments, turning physics into a kind of watchmaking on a cosmic scale. By the 1890s, Michelson had become recognized worldwide as the authority on precision optics. He expanded his work into the measurement of fundamental lengths. With his interferometer, he could measure distances smaller than a millionth of a meter, using the wavelength of light itself as a yardstick. This technique allowed him to refine the definition of the meter, anchoring it not to a metal bar in Paris, but to the vibrations of nature's own light. Such a shift was revolutionary, for it meant that units of measurement could be tied to universal constants rather than to fragile artifacts. The interferometer, Michelson's greatest invention, proved versatile beyond even his hopes. By combining beams of light and allowing them to interfere, he created fringes of dark and bright lines that shifted with the slightest change in distance. This sensitivity opened entire new fields. With it, he measured the diameters of stars, resolving for the first time that Betelgeuse and other giants were not mere points, but disks of light. It was a feat once thought impossible, an astronomical leap achieved not with telescopes alone, but with the physics of interference. Despite these triumphs, Michelson remained haunted by the ether. The null result of the Michelson-Morley experiment had unsettled the foundations of physics. He himself was reluctant to abandon the ether altogether. Like many of his generation, he believed that waves must have a medium, that light could not ripple in emptiness. For years, he sought ever more refined experiments, hoping perhaps that the elusive ether drift might at last be revealed. Yet each repetition returned the same result: silence. The fringes refused to shift. The ether, if it existed, was invisible beyond all detection. The cultural impact of Michelson's work was immense. Newspapers hailed his experiments as proof of American scientific maturity. At a time when Europe still dominated the intellectual landscape, here was an American physicist rivaling the greatest laboratories of Paris and Berlin. His Nobel Prize in 1907 was celebrated as a national triumph, proof that the new world could equal the old in the precision of science. Among his peers, Michelson was admired not for bold theories, but for the patient artistry of experiment. Where others proposed sweeping ideas, he perfected the instruments that put those ideas to the test. His work embodied the 19th century spirit of measurement, the belief that nature would yield its secrets, not through speculation, but through numbers fixed to as many decimals as possible. Yet the implications of his precision reached far beyond his own intentions. The stubborn constancy of the speed of light in his interferometers, regardless of direction, prepared the way for Einstein's bold leap in 1905. Without Michelson, Einstein might not have had the puzzle of ether drift to resolve. nor the firm numerical foundation upon which to build his principle of relativity. Michelson had not set out to change our conception of space and time, but his experiments made that revolution possible. By the turn of the century, thanks to Michelson's tireless refinements, the speed of light was pinned down to within a few kilometers per second. For all practical purposes, it had become a constant of nature, as reliable as the acceleration of gravity or the length of the day. Michelson himself continued to dream of greater accuracy, planning vast experiments that would stretch across mountain valleys, with mirrors stationed miles apart. He never ceased in his pursuit, convinced that perfection was always one more refinement away. His name became a symbol of exactitude. To speak of Michelson was to speak of the highest standards of measurement. His instruments carried physics into a new age, an age where constants were not merely guessed, but known, not approximated, but fixed to decimals that future generations would inherit. The torch of measurement had been passed from Galileo's crude lanterns and Roemer's distant moons to the laboratory precision of polished mirrors and controlled baselines. But even Michelson's genius could not escape the larger tide. The ether that he had sought so long to detect would not survive the century. Einstein would abolish it altogether, replacing it with the far stranger notion that space and time themselves shifted and stretched to preserve the constancy of light's speed. Michelson had given the number. Einstein would give it meaning. Michelson's later years were marked by an unrelenting pursuit of perfection. Even after winning the Nobel Prize, he believed the speed of light could be fixed to greater accuracy, and he launched ever more ambitious projects to achieve it. He built experimental baselines across mountain valleys, using mirrors stationed miles apart to extend the path of the light beam. He carried his apparatus to mountain tops, where thinner air reduced distortion, and he refined his interferometers until they could detect shifts smaller than a tenth of a wavelength of light. These efforts produced numbers of astonishing precision. By the early 20th century, the speed of light was pinned down to within a few parts in 100,000, an accuracy that rivaled any constant then known. For practical science, the value was now reliable enough to serve as a standard, and for theoretical physics, it became a cornerstone. Maxwell's equations of electromagnetism, already elegant, now had experimental confirmation to the highest degree. The velocity predicted by the equations matched Michelson's measurements almost exactly, a convergence of theory and experiment that thrilled the scientific world. Yet Michelson himself did not embrace the revolution that his results helped to ignite. He remained, to the end of his life, attached to the concept of the ether. He continued to design ever more sensitive interferometers, hoping that some faint trace of ether drift would finally appear. But the fringes remained still, year after year, experiment after experiment. Nature refused to yield what he sought. In his notebooks and letters, he expressed disappointment, but also resolve. He was a man of instruments, not of theories, and he left to others the task of interpreting what his results implied. It was Albert Einstein who gave those results their true meaning. In 1905, Einstein proposed that the constancy of the speed of light was not a curiosity, but a law of nature, valid for all observers, regardless of their motion. From that principle, he derived special relativity, dissolving the ether entirely and reshaping space and time themselves. What Michelson had treated as an unsolved puzzle, Einstein elevated into a universal truth. The speed of light was no longer just a measured velocity, it was the cosmic speed limit, the link between energy and mass, the constant that defined space-time itself. Michelson lived to see the early years of relativity, though he never fully accepted its radical ideas. He remained devoted to the craft of measurement, continuing to refine his numbers until his death in 1931. By then his name had become a monument in physics, synonymous with exactitude. Generations of scientists built upon his work, and the instruments he pioneered, interferometers, would later detect the ripples of space-time itself in the form of gravitational waves. a triumph beyond anything Michelson could have imagined. Thus, the age of precision that he embodied reached both backward and forward in history. Backward, it closed the long arc from Galileo's lanterns to the laboratories of the 19th century, proving once and for all that light speed was finite and measurable. Forward, it opened the door to Einstein's relativity and to the modern age of physics, where the constant c is no longer a mystery, but a foundation of reality. Michelson had turned the velocity of light into one of the most precisely known quantities in the world. In doing so, he gave science the key that would unlock an entirely new vision of the cosmos. The beginning of the 20th century was a time of both triumph and unease in physics. Maxwell's equations had unified electricity and magnetism into a single theory, and Michelson's precision measurements had confirmed that the speed of light was fixed and astonishingly stable. Yet this very stability posed a riddle. If light was a wave, and all waves required a medium, where was the ether that carried it? Michelson and Morley had searched for the drift of the ether with their interferometer and found nothing. Light seemed indifferent to the Earth's motion, always racing at the same speed in every direction. The experiment that was meant to confirm the ether instead cast doubt on its existence. It was into this tension that Albert Einstein stepped in the year 1905, a young patent clerk in Bern, unknown to most of the scientific world, but filled with ideas that would reshape reality. In that year, often called his annus mirabilis, his miracle year, he published a series of papers that altered physics forever. Among them was his work on what he called the electrodynamics of moving bodies. In it, he proposed a radical idea. The speed of light is not only finite, but also absolute, the same for all observers, regardless of how they move. The proposal was as daring as it was simple. For centuries, scientists had assumed that space and time were fixed backgrounds, universal stages upon which events played out. Speeds added and subtracted in ordinary ways. If a carriage moved forward and a man walked inside it, his pace relative to the ground was the sum of both motions. Yet light refused to obey this logic. Michelson had shown that no matter how the Earth moved, the speed of light remained constant. Einstein took this fact not as a puzzle, but as a principle. He declared that nature was built in such a way that the velocity of light, c, was the same in every frame of reference. The consequences were astonishing. If the speed of light was fixed, then space and time themselves must bend to preserve it. Lengths would contract for objects in motion, times would dilate, simultaneity would dissolve into relativity. The rigid stage of Newton's universe crumbled, replaced by a flexible fabric in which observers moving at different speeds lived in different slices of reality. What bound them all together was c, the constant speed of light. It became not just the velocity of a wave, but the ultimate limit of motion, the very structure of space-time. Einstein's paper made clear that no signal, no matter, no information could travel faster than light. It was the cosmic speed limit, the horizon that nothing in the universe could cross. Particles might accelerate, energies might grow without bound, but as they approached c, the demands of relativity became infinite. To reach light speed would require infinite energy, and so it could never be done. Light itself, massless and eternal, alone traveled at c, while all other things were confined beneath it. This shift was philosophical as much as physical. For millennia, light had been treated as an exception, either instantaneous or too swift to measure. Now it became the rule, the measure by which all motion was judged. It was not simply a property of illumination, but a constant of the cosmos, binding space and time together. The number 299,792 kilometers per second ceased to be just a measurement. It became the foundation of physics, a value so fundamental that it defined what it meant to move, to age, to exist in space-time. At first, many struggled to accept it. The idea that time could run differently for different observers seemed absurd. How could one person's seconds be longer than another's? How could rulers shrink simply by moving? But experiments soon confirmed Einstein's predictions. Clocks carried on fast trains, or later on airplanes, did indeed tick differently. Particles in accelerators lived longer than their stationary counterparts. Every test affirmed that the strange rules of relativity were real, and at their core lay the constancy of c. Einstein himself saw the beauty of the principle. It was not a complication, but a simplification, an economy of nature. By holding the speed of light fixed, the universe forced space and time to adapt, unifying them into a single continuum. Out of this insight grew special relativity, and from it, eventually, the equation E equals mc squared, showing that mass and energy were interchangeable, bound together by the constant that light defined. In the span of a single year, the swiftness of light had been transformed from a number measured with mirrors to the constant that shaped the universe. The cosmic speed limit was no longer just a curiosity of optics, but the heartbeat of reality itself. The lanterns of Galileo, the moons of Roma, the tilted stars of Bradley, the spinning mirrors of Foucault, the interferometers of Michelson, all of these had prepared the way. But it was Einstein who took the final step, declaring that light speed was not merely a fact to be measured, but the law by which space and time themselves must live. Einstein's declaration that the speed of light was the same for all observers was at first met with skepticism, even bewilderment. The idea clashed with common sense and with the habits of thought built up over centuries of classical physics. In Newton's world, a clock ticked the same for all. A meter stick was the same length everywhere, and events had absolute order. But in Einstein's world, clocks slowed when they moved, rulers shortened along their direction of travel, and simultaneity itself dissolved into relativity. Two observers racing past one another might disagree on which events happened first, yet both would be correct within their own frame. To many, this seemed a violation of reality itself. But Einstein was not content to rest on abstraction. He made predictions, concrete and testable, that could decide the matter. Moving clocks, he said, would run slow. This was time dilation, a stretching of duration for objects in motion. Rulers in motion would contract along their length, a shrinking imperceptible at ordinary speeds, but measurable at velocities approaching that of light. And energy itself was no longer separate from mass. With the equation E equals mc squared, Einstein announced that a small amount of matter contained an enormous reservoir of energy, released only if the mass were converted entirely. The implications were staggering. If these predictions were borne out, then the speed of light was not just a limit on motion, but a link between the fabric of time and the essence of matter. And soon enough, experiments began to confirm them. In the years after Einstein's paper, physicists studying fast-moving particles noticed that they decayed more slowly when accelerated. Muons, unstable particles born in cosmic rays high in the atmosphere, survived to reach the Earth's surface only because their internal clocks were slowed by their near-light speeds. This was time dilation made manifest, a direct proof of Einstein's claim. Another confirmation came from accelerators. As particles were pushed to higher and higher velocities, the energy required to increase their speed grew without bound. They could approach the speed of light, but never reach it. The machines confirmed what the equations demanded. Light speed was a horizon, absolute and uncrossable, the wall of nature. Nothing with mass could touch it. For philosophers, the shift was profound. Time and space were no longer absolutes. They were woven together into space-time, a four-dimensional fabric where distances in time could trade with distances in space, bound by the speed of light. The very structure of reality had become dynamic. Observers did not share a single universal present, but carried with them their own private nows, stitched together by sea. This was not a universe of instantaneity, nor a universe of fixed absolutes, but one where light itself defined the limits of what could be known and what could be shared. Einstein's insight also closed a circle that had begun centuries earlier. Galileo had wondered whether light was instantaneous, testing it with lanterns. Roma had shown its finitude in the tardiness of moons. Bradley had confirmed it in the tilt of stars. Fizeau, Foucault, and Michelson had pinned it down with mirrors and wheels. Now Einstein revealed why it mattered. The speed of light was not a curious measurement, but the very scaffold of space-time. It was the constant that united energy with mass, that set the boundary between cause and effect, that made the universe coherent. The more scientists tested relativity, the stronger it became. Observations of fast particles, precise measurements of time, and later even the synchronization of atomic clocks aboard airplanes confirmed Einstein's predictions again and again. Every experiment strengthened the cosmic law. The speed of light is the same for all observers, and nothing can outrun it. By the 19-teens, the revolution had spread. Physicists, once skeptical, began to adopt the new framework. Philosophers debated its implications for causality and determinism. Writers marveled at its strangeness. The world of everyday experience remained unchanged, but beneath it lay a deeper order, revealed only when speeds approached that of light. Einstein had transformed the mystery of swiftness into a universal principle. In this new vision, the constant c was not only a number, but the heartbeat of the cosmos. It was the thread that connected time, space, matter, and energy into one fabric. Light, once thought instantaneous and ethereal, was now the measure of all things, the ultimate limit, the law that even the universe itself must obey. Einstein's vision of light as the ultimate speed limit rippled outward across every corner of physics. The constancy of c was no longer just about beams in mirrors or telescopes aimed at stars. It was about the way the universe itself operated. If nothing could surpass the speed of light, then the order of cause and effect was preserved. A signal from one event could not arrive before its cause unless it traveled faster than light, and that was forbidden. The cosmos was safeguarded against paradox by the very swiftness of light. As the years passed, relativity became more than a theory of moving bodies. It became a new geometry of the universe. Hermann Minkowski, a mathematician who had once taught Einstein, reformulated relativity into a four-dimensional continuum of space-time. In this framework, the distance between events combined space and time into a single measure, and the speed of light emerged naturally as the conversion factor between them. Seconds could be translated into kilometers, and kilometers into seconds, by multiplying with c. Light was no longer just a wave or a particle. It was the yardstick by which the universe measured itself. Experiments multiplied, each confirming the principle. Atomic clocks carried on aircraft or satellites ticked differently according to their speeds and altitudes, just as relativity predicted. Particles accelerated to near light speed lived far longer than their stationary lifetimes, confirming time dilation in the laboratory. The symmetry of c underlay the design of every accelerator and every high-energy experiment. What had once been a speculative principle became the daily working reality of modern physics. The philosophical consequences deepened. The constancy of light meant there was no absolute rest, no universal frame of reference. Each observer carried their own grid of space and time, and all were equally valid. The cosmos was democratic in this sense, no viewpoint privileged above another. What bound them together what all could agree upon was the speed of light. It was the one invariant, the one fixed quantity in a universe where everything else was relative. Einstein himself marveled at the simplicity of it. He once remarked that the happiest thought of his life was the realization that a person falling freely would feel no gravity. From that insight, he would go on to general relativity, where space-time itself curved around masses, guiding the paths of planets and light alike. But even in that grander theory, the speed of light remained central. It was still the limit, still the constant, still the heartbeat of the cosmos. By the 1920s, the transformation was complete. Light's velocity had been measured with Michelson's mirrors, confirmed by Einstein's relativity, and woven into the very definition of space-time. What had begun as a philosophical puzzle in ancient Greece was now a universal law. The speed of light was not only finite, it was foundational. It was the boundary of motion, the link between energy and mass, the constant that defined reality itself. The torch would soon pass to the next chapter, where physicists would no longer merely measure c, but redefine their very units around it. The meter itself would one day be defined by the distance light traveled in a fraction of a second. From mystery to measurement to definition, light's speed would become not just a number, but the universal standard by which all else was judged. By the middle of the 20th century, the speed of light had journeyed from a philosophical speculation to one of the most carefully measured quantities in all of science. Fizeau's toothed wheel, Foucault's spinning mirror, and Michelson's monumental interferometers had refined the number until it stood at 299,792 kilometers per second, with uncertainties shrinking decade by decade. Einstein had elevated that number from a physical property of light to the foundation of space-time itself. Yet the story was not finished. Precision instruments of the modern era would take the pursuit even further, until the very definition of length was tied not to a bar of metal, but to the flight of light across a fraction of a second. The push came with the arrival of new technologies. Lasers, developed in the 1960s, provided beams of light far more coherent, stable, and intense than anything available before. Where earlier experiments had relied on flickering lamps or arc sources, lasers gave physicists a tool of nearly perfect steadiness. Their beams could be directed across long baselines without divergence, their frequencies locked and measured with extraordinary accuracy. Interferometry, already Michelson's realm of mastery, was reborn with laser light, offering sensitivity far beyond the mirrors of the 19th century. With these tools, scientists refined the value of C to astonishing precision. In 1972, researchers at the United States National Bureau of Standards measured the speed of light using a laser frequency stabilized by molecular absorption lines. Their result was accurate to a few meters per second. 3 years later, in 1975, a consensus value was announced: 299,792.45.8 kilometers per second, with an uncertainty of only 1 meter per second. For the first time, the swiftness of light was known to within less than 1 part in 100 million. At that level of refinement, the situation reversed. For centuries, the meter had been defined by a platinum iridium bar kept in Paris, an artifact vulnerable to thermal expansion, scratches, or slight deformation. Measurements of C were expressed in terms of that bar. But by the late 20th century, the speed of light could be determined far more accurately than the length of the meter bar could be maintained. The dependent had become the master. Scientists realized that instead of defining C by the meter, they could define the meter by C. In 1983, the General Conference on Weights and Measures made the historic decision. The meter would no longer be the length of a bar in Paris. It would be the distance that light travels in vacuum in 1/299,792,458 of a second, In this definition, the speed of light was fixed exactly at 299,792 kilometers per second. It was no longer a measured quantity, but a defined constant, as fundamental as the number of seconds in a day. This was more than a technical adjustment. It marked a profound shift in philosophy. For centuries, humanity had struggled to measure the speed of light, to pin it down from infinite to finite, from approximate to precise. Now, the struggle had ended not with yet another refinement, but with a redefinition of reality itself. The speed of light was no longer something to be determined. It was the standard by which all other lengths and times were judged. The chase was over because the quarry had been elevated into law. The change rippled outward into science and technology. With C fixed, the meter became tied directly to the second, which itself was defined by the vibrations of atoms in cesium clocks. The foundations of measurement now rested not on artifacts of matter, but on constants of nature. Any laboratory in the world, with the proper equipment, could reproduce the standard by measuring the time light took to traverse a known interval. Measurement had become democratic, universal, liberated from the fragility of a single object in Paris. For physics, the consequences were equally deep. The elevation of C to a defined constant symbolized its role as a fundamental feature of the cosmos. Alongside Planck's constant and the gravitational constant, it became one of the cornerstones upon which the edifice of modern science was built. Every equation of relativity, every calculation in quantum field theory, every design of a satellite or a laser relied upon its exact value. From the timing of GPS signals to the synchronization of clocks in particle accelerators, the constancy of C was woven into the daily fabric of technology. It was a moment of closure in a story stretching back 2,000 years. The philosophers of antiquity had asked whether light was instantaneous or delayed. Galileo had tried to measure its flight with lanterns, Romer with moons, Bradley with stars, Fizeau and Foucault with wheels and mirrors, Michelson with interferometers. Each had brought the number closer to truth. Einstein had shown why the number mattered, turning it into a limit of nature. And now, the 20th century had brought the journey to its end by defining the very units of space around it. The torch would not be extinguished, however. Though the speed of light was fixed by definition, scientists continued to test its constancy with ever greater rigor. They sought to confirm that C was the same for all frequencies, for all directions, for all conditions of space. Gamma-ray bursts from distant galaxies, pulses from neutron stars, and beams from particle accelerators became laboratories for checking the invariance of light speed. At cosmic distances and in extreme energies, the constant continued to stand firm. Thus, the story of light speed had traveled from mystery to measurement to definition. What had once been an elusive quarry had become the universal yardstick, the heartbeat of modern science. The pursuit that began with myth and speculation ended in certainty. The number was now eternal, written not only in the equations of physics, but in the very structure of how humanity measured its world. The arrival of the laser was like giving physicists a perfectly tuned instrument after centuries of playing by ear. Where earlier light sources wavered in frequency and flickered in brightness, the laser produced a beam of such stability and coherence that it seemed almost like a ruler made of light itself. A beam could travel kilometers without losing its focus, its waves aligned in lockstep like soldiers marching in perfect formation. For interferometry, this was nothing short of a revolution. Where Michelson had once strained to keep arc lamps steady, now scientists could use beams so precise that even the smallest shifts became visible. With this tool, laboratories around the world began competing to refine the measurement of light's velocity. In Boulder, Colorado, at the National Bureau of Standards, researchers locked lasers to the spectral lines of molecules. Each frequency was like a clock, ticking billions of times each second with unerring regularity. By measuring the wavelength of the light and multiplying by the frequency, the speed of light could be determined with a precision unimaginable only decades earlier. Across the Atlantic, in Paris and London, physicists carried out similar experiments, each pushing the uncertainty smaller and smaller. These efforts converged in the mid-1970s, when the value of c was announced with a precision better than 1 meter per second. To the casual eye, this may have seemed unnecessary. What difference could a meter per second make in something that already moved 300,000 kilometers in that time? But for physics, the difference was profound. The stability of atomic clocks meant that time could be measured to parts in a trillion, and so the definition of length had to match. It would no longer do to keep a bar of platinum iridium in a vault and declare it the standard. The future of measurement demanded universality, reproducibility, and freedom from artifacts of matter. The decision of 1983 was the culmination of this logic. By tying the meter directly to the speed of light, the world of metrology took a step that was both radical and natural. Radical because it redefined one of humanity's oldest units, not by a physical object, but by a property of the universe. Natural because by then the precision of c had outstripped the precision of the meter bar, and the only consistent choice was to invert the relationship. Light itself became the ruler. The announcement carried a sense of finality, as though a centuries-long chase had ended. Scientists no longer asked, "What is the speed of light?" Instead, they declared, "This is the speed of light, and by it we define our measures." The number was no longer an approximation, but an axiom. It was the scaffolding upon which all measurement rested. Just as the number of degrees in a circle is not discovered but chosen, so too the speed of light became fixed by definition, anchoring the meter forever. In laboratories, the change transformed practice. Rather than calibrating rods or bars, researchers turned to time. The second was already defined by the oscillations of cesium atoms, which ticked with a precision unmatched by any mechanical clock. Combine that with the exact speed of light, and length could be realized anywhere on Earth with lasers and electronics. A meter was no longer something that had to be compared to a master copy in Paris. It could be recreated in any laboratory, in any country, with instruments tuned to the rhythm of atoms and the flight of light. Measurement had become global and universal. Philosophically, the step resonated. For millennia, humanity had struggled to grasp the nature of light, debating whether it was instantaneous or finite, particle or wave. Now, not only was its speed known, but that speed had become the cornerstone of reality's very measurement. The pursuit that began with questions of vision and geometry had culminated in a law so fundamental that it defined how we measure space itself. It was as though light had moved from being a messenger of the universe to being its metric, the very language in which reality was written. And yet, the redefinition did not end curiosity. Physicists continued to test whether c was truly constant in all conditions. Did gamma rays from distant explosions arrive at the same time as lower energy photons? Did light bend or slow in ways not predicted by relativity when crossing the depths of interstellar space? Each test confirmed the same answer: the constant held. The universe, in its vastness and complexity, obeyed the law of light speed with unyielding fidelity. The story had shifted. Light was no longer the subject of measurement, but the standard of it. The age of uncertainty had given way to the age of definition. Humanity had taken the swiftness of light, once elusive and mysterious, and placed it at the very center of knowledge, fixing it as the yardstick by which all space is measured. The decision of 1983 to define the meter by the speed of light did more than tidy up the world of measurement. It rippled outward into science, engineering, and daily life in ways that touched nearly every technology of the late 20th century. By fixing c as exact, scientists had placed a universal rhythm into the very foundation of civilization. One of the clearest examples was navigation. The global positioning system, developed in the 1970s and 1980s, relied on satellites broadcasting signals timed by atomic clocks. A receiver on Earth measured the delay between those signals to calculate its position. But the calculation assumed a speed of transmission, and that speed was the velocity of light. With c fixed and exact, GPS could pinpoint locations to within meters and later, with refinements, within centimeters. The system that guides airplanes, maps roads, and synchronizes financial transactions depends at its core on the constancy of light speed as defined in 1983. Space exploration too was transformed. Communication with distant probes, Voyager, Cassini, New Horizons, depends on timing signals across billions of kilometers. Each command takes hours to arrive, each image hours to return. All calculated by the unyielding swiftness of c. By defining light speed exactly, mission planners could predict delays and trajectories with unmatched accuracy, ensuring that spacecraft millions of kilometers away responded to instructions with clockwork precision. The cosmic messenger became not only a tool of discovery, but the ruler by which humanity stretched its reach across the solar system. In laboratories, interferometers of extraordinary sensitivity were built upon Michelson's legacy. These instruments, now armed with lasers, stabilized to parts in a trillion, measured displacements smaller than a proton. They became the detectors that, a century after Michelson's death, would confirm Einstein's general relativity by observing gravitational waves. When the waves passed through Earth in 2015, they stretched space itself by less than 1 part in 1,000 billion. Only by trusting the fixed and exact speed of light could scientists interpret those ripples as the songs of colliding black holes. Philosophically, the redefinition symbolized a final reversal of perspective. For most of history, humanity had asked, how fast does light travel? By the close of the 20th century, the question had been answered so thoroughly that it ceased to be a question at all. Instead, the new question became, how do we use the speed of light to define everything else? Distance, once measured by rods, ropes, or celestial triangulation, was now measured by time itself, the time light took to cross a given span. The second, set by the oscillations of cesium atoms, became the anchor, and the meter, a derived quantity, inseparably linked to c. It was a fitting end to a long pursuit. From myth to speculation, from moons and stars to wheels and mirrors, from interferometers to lasers, the chase had always been for greater certainty. By 1983, certainty was absolute. The speed of light was no longer hunted, no longer subject to experiment or revision. It was the law by which all else was measured, the constant not only of relativity, but of human understanding itself. Yet the transition was not closure, but opening. Fixing c did not halt science, it empowered it. Freed from the need to chase decimals, physicists could now turn to cosmic tests, probing whether the constant held across the universe and through extremes of energy. Gamma-ray bursts, pulsars, and quasars became laboratories on a galactic scale, each one a test of light's unwavering swiftness. The laboratory experiments of the 19th and 20th centuries had ended, but the cosmic experiments of the 21st were just beginning. Thus, the story of light speed had completed one arc and begun another. It had traveled from mystery to measurement to definition, from lanterns to lasers, from wonder to standard. Humanity now carried it as a tool, a ruler, a law. It was the heartbeat of physics, the pulse of technology, the measure of space and time. And even as it became fixed, it continued to inspire, reminding us that behind every constant lies a history of questions, experiments, and the relentless human desire to know. By the close of the 20th century, the speed of light had ceased to be a measurement and had become a definition. The meter was tied to it, the second anchored it, and the constant c was woven into the very language of physics. Yet science does not end at definition. A number may be fixed in our system of units, but nature itself must still be tested. Was the speed of light truly the same everywhere and for every kind of radiation? Could the universe, vast and ancient, reveal variations that no laboratory on Earth could detect? With telescopes aimed to the farthest reaches of space, physicists sought to test c on a cosmic scale. The first arena was the light of exploding stars. Supernovae, those cataclysmic deaths of massive suns, released bursts of radiation across the spectrum, from radio waves to gamma rays. If the speed of light were not constant, if higher energy photons raced faster or slower than their lower energy kin, then the light curves of these explosions would arrive smeared across time. But the pulses came together, their peaks aligned, no matter the distance. From galaxies millions of light years away, the photons arrived shoulder to shoulder, as though reminding us that c was not negotiable, not even across the gulfs of intergalactic space. Pulsars offered another cosmic laboratory. These neutron stars, the collapsed remnants of supernovae, rotated with clock-like precision, sending beams of radiation sweeping across the cosmos. When a pulsar's beam passed Earth, it arrived as a tick, a cosmic metronome that rivaled the steadiness of atomic clocks. If different frequencies traveled at different speeds, the ticks would scatter, smeared into blurs. Yet even across thousands of light years, the pulses remained sharp. Radio waves, X-rays, and gamma rays all traveled at the same swiftness. The universe itself seemed to conspire with Einstein, affirming that the constant of light was inviolate. Perhaps the most dramatic tests came from gamma ray bursts, the most energetic explosions known. In distant galaxies, collapsing stars or colliding neutron stars released torrents of radiation in flashes that outshone entire galaxies. Detectors on Earth caught these bursts with exquisite timing, measuring the arrival of photons spanning energies millions of times apart. If c wavered even by a part in a trillion, the bursts would unravel. But again, the photons arrived together, their journey through billions of light years marked by unbroken constancy. Gravitational lensing provided yet another test. According to Einstein's general relativity, light passing near a massive body bends, its path curved by space-time itself. In the cosmos, galaxies and clusters of galaxies act as lenses, bending the light of objects behind them. When a distant quasar lies behind such a lens, its light may split into multiple paths, arriving at Earth as separate images. By measuring the differences in arrival time, astronomers can test whether all light, regardless of path or energy, travels at the same speed. The verdict was always the same. C held true. In 2017, an extraordinary opportunity arrived. A pair of neutron stars collided in a galaxy 130 million light-years away. The merger released both gravitational waves, ripples in space-time itself, and a burst of light across the spectrum. Detectors on Earth caught both signals, separated by less than 2 seconds, despite their immense journey. If gravitational waves had traveled at a different speed than light, the difference should have accumulated into years or centuries. Instead, they raced neck and neck, confirming that even across cosmic distances, the speed of light matched the speed of space-time's own ripples. These cosmic confirmations were more than tests of relativity. They were affirmations that the constant chosen as the foundation of physics truly was universal. The definition of the meter by c was not an arbitrary convention, but a reflection of the universe's own fidelity. From the death of suns to the collision of stars, from the ticking of pulsars to the explosions of galaxies, Every signal whispered the same truth. The speed of light is unchanging. Yet scientists did not stop searching. Theories of quantum gravity, attempts to unify relativity with the quantum world, sometimes suggested that at extreme energies or tiny scales, the constancy of C might falter. Perhaps the very fabric of space-time, grainy and foamy at the Planck length, could slow or hasten photons depending on their energy. If so, the first hints would appear in the timing of cosmic bursts. To date, no such deviation has been seen. The constant remains constant, even when tested against the most violent furnaces of the universe. Thus, the story of light's speed extended from laboratories on Earth to the farthest corners of the cosmos. What began as an argument among philosophers about instantaneity had become a principle tested by supernovae, pulsars, and colliding stars. Each cosmic laboratory reaffirmed what Galileo, Rømer, Bradley, Fizeau, Foucault, Michelson, and Einstein had suspected. Light does not falter. It travels at the same pace everywhere, across every distance, for every frequency. It is not only the heartbeat of physics, but also the rhythm of the universe itself. Cosmic confirmations of light's constancy became more intricate as astronomers turned their eyes toward the most distant and complex structures in the universe. Quasars, the blazing cores of young galaxies powered by supermassive black holes, provided one of the most dramatic natural experiments. Their light traveled for billions of years, often bending around intervening galaxies that acted as gravitational lenses. When the quasar's light split into multiple images, each path took a different route through curved space-time, arriving at Earth with delays ranging from days to years. Yet within each image, the photons of differing energies all kept pace, their signals aligned to exquisite precision. If C had varied even slightly over cosmic time or across frequencies, the evidence would have appeared in these delays. Instead, the lensed quasars confirmed that light's swiftness was the same across every path. Astronomers also studied cosmic background radiation, the faint afterglow of the Big Bang. These microwaves filled the sky uniformly, a relic of the universe when it was only a few 100,000 years old. Subtle ripples in this background were mapped with satellites, revealing variations that carried the signature of light's propagation through the early plasma of the cosmos. Had the speed of light shifted even slightly during that primordial epoch, the entire pattern of ripples would have been distorted. Instead, the data fit perfectly with Einstein's framework. Light had raced across the newborn universe with the same constancy it displays today. As telescopes advanced, the search grew more daring. When astronomers measured rapid flares from blazars, galaxies with jets pointed directly at Earth, they timed arrivals across the electromagnetic spectrum to fractions of a second. Some photons carried energies millions of times greater than visible light, yet still they arrived alongside their lower energy kin. If space-time had a hidden graininess, as some quantum gravity theories proposed, then high-energy photons might lag behind. No such lags appeared. The universe had been generous enough to let us test its constancy across unimaginable scales, and each test reaffirmed the same unyielding law. The philosophical weight of these results was immense. They showed that C was not merely a human definition, an artifact of metrology, but a truth written into the structure of the universe itself. From the flash of supernovae to the echo of the Big Bang, from quasars to neutron star collisions, every signal carried the same message. Light travels at one speed in vacuum, regardless of its energy, its path, or the epoch of cosmic history. The constancy of C was as universal as the stars themselves. These cosmic verifications also sharpened our view of the possible limits of relativity. If Einstein's theory were ever to break, it would likely reveal itself at the extremes. The highest energies, the earliest times, or the longest distances. That is why physicists scrutinized gamma-ray bursts and pulsars with such care, hoping for the faintest hint of deviation. None has been found, but the search continues, for even a single photon arriving late could herald a revolution. The absence of such anomalies is itself remarkable, a testament to how deeply woven light speed is into the fabric of reality. By testing C-on scales no laboratory could ever replicate, astronomers transformed light into a cosmic probe. Each photon that traveled across billions of years carried within it a silent affirmation of Einstein's principle. Each signal arriving in unison, each burst echoing across space, stitched together the universe's grandest structures with the thread of constancy. What once was measured with lanterns and mirrors was now confirmed by galaxies and explosions, by the deepest time and the farthest distance. The 21st century brought with it the most dramatic tests yet of light's cosmic fidelity. Astronomers had long compared photons of different energies, but now a new messenger arrived: gravitational waves, ripples in space-time itself. When detectors like LIGO first opened their arms in 2015, they were tuned to sense displacements smaller than a proton's width, caused by waves that had traveled across hundreds of millions of light-years. These ripples, predicted by Einstein, moved at the speed of light, at least according to relativity. But nature would have to confirm it. In August of 2017, confirmation arrived in spectacular fashion. A pair of neutron stars spiraled into one another in a galaxy 130 million light-years away. The collision sent gravitational waves racing outward, caught on Earth by LIGO and Virgo, while telescopes across the world detected a brilliant burst of light. The two signals arrived almost together, separated by less than 2 seconds, despite traveling for 130 million years. If the speed of light and the speed of gravity had differed by even 1 part in a quadrillion, the signals would have been staggered across centuries. Instead, they arrived in near-perfect synchrony. It was a cosmic chorus, affirming that Einstein's prediction held not only for light, but for space-time's own waves. The event marked the dawn of multi-messenger astronomy, where different signals, light, gravitational waves, neutrinos, are compared to probe the universe. Each messenger has its own nature, but all must obey the same cosmic speed limit. In every case so far, the verdict has been the same: C is unyielding, a constant across the deepest gulfs of space and the most violent explosions of time. Physicists, however, remain restless. Theories that attempt to unify relativity with quantum mechanics often predict that space-time is not smooth, but foamy, grainy at scales near the Planck length, which is about 10 to the power of -35 meters. If so, photons of different energies might interact differently with that microscopic graininess, leading to minuscule differences in their speeds. To test this, astronomers scrutinize gamma-ray bursts and blazars, timing the arrival of photons with energies billions of times greater than visible light. So far, no cracks have appeared. If space-time is grainy, its influence is subtler than our most sensitive instruments can yet detect. This constancy, so stubborn and so universal, has become a compass for modern physics. The unchanging speed of light is not only a limit, but also a promise that the universe can be trusted to carry signals faithfully across unimaginable distances. It underpins our navigation systems, our synchronization of time, our exploration of the cosmos, and our search for new physics. Each photon and each ripple of gravity that arrives on time is a reminder that C is still the foundation upon which reality rests. And yet the search continues, because science never stops at certainty. Each new telescope, each new detector, each new burst from the cosmos provides another chance to test the constancy of light. The The quest that began with questions of vision in ancient Greece has stretched to the edges of the observable universe, and still the same answer comes back. Light, the most elusive and swift of all messengers, travels at one speed only, and in doing so, it binds the universe together. Thus, the cosmic tests of the 21st century close one arc of history and open another. From Galileo's lanterns to Einstein's relativity, from Reaumur's moons to LIGO's ripples, the speed of light has been measured, confirmed, defined, and tested on scales beyond imagination. It is both the heartbeat of physics and the silent metronome of the cosmos. As humanity listens to the universe's deepest signals, it hears again and again the same refrain: light speed is constant, unbroken, and eternal. The history of light speed is not merely a tale of experiments and numbers. It is also a story of shifting worldviews, of how humanity's perception of the cosmos transformed each time a new truth about light emerged. From the earliest whispers of philosophy in ancient Greece to the laboratories and observatories of the modern age, each step in the journey forced us to reconsider our place in the universe. The progression from instantaneous light to finite light, and finally to light as the very fabric of space and time, is one of the most profound philosophical evolutions in human thought. In the ancient world, the question of whether light was instantaneous was more than a scientific curiosity. It was tied to metaphysics, to ideas of perfection and divinity. Aristotle believed that vision was immediate, an act of contact between the eye and the object, for the heavens themselves could not be delayed. For thinkers steeped in notions of celestial perfection, the idea of light taking time to travel seemed almost sacrilegious. To suggest that there was a delay between cause and perception would mean that the senses could not be trusted, that the heavens were not eternal but subject to time. Thus, the instantaneous view prevailed for centuries, more as a philosophical necessity than as a measured fact. During the medieval era, light became entwined with theology. It was the symbol of divine presence, of truth, of revelation. Thinkers like Augustine and Aquinas spoke of light as the medium by which God illuminated the human mind. Its speed, whether finite or infinite, was less important than its symbolic role. In this way, light became a metaphor as much as a phenomenon, an idea more than a measurable entity. Yet even then, scholars such as Alhazen began to consider the mechanics of vision and optics, hinting that light might be subject to laws as physical as any stone or river. The Renaissance rekindled the curiosity of measurement. Galileo, with his lantern experiment, sought to test what had long been taken on faith. His failure to detect a delay did not confirm infinity, but it demonstrated that the question could be asked with instruments, not just philosophy. This marked a subtle shift. Light was no longer purely divine or metaphysical. It was becoming a natural phenomenon, subject to experiment. The philosophical implication was immense. If light could be tested, so could anything. Nature itself could be interrogated, and the answers would come not from scripture or speculation, but from observation. Reaumur's revelation in the 17th century dealt a heavy blow to the ancient view. When he declared that the moons of Jupiter revealed light's finite speed, the cosmos itself seemed to tremble. For the first time, humanity faced the idea that sight was not immediate. To see was to look into the past, however briefly. The philosophical shift was profound. If light took time to travel, then the heavens were not what they seemed in the present moment. The stars overhead were ancient, their light delayed. The universe was not immediate, but historical, a record of past events carried on beams of light. This realization forever altered humanity's relationship with the night sky. Bradley's confirmation with stellar aberration reinforced this truth. The universe was not fixed, and still but dynamic, with Earth rushing through space and the stars' positions tilting in response. For philosophy, This meant that reality was not absolute, but relative to motion and perspective. The seeds of relativity were planted not in Einstein's era, but in the 18th century, when observers realized that the cosmos looked different depending on one's motion. Humanity's vision was revealed to be partial, shaped by the velocity of the observer, and no longer universal. The 19th century brought a different shift. Fizeau, Foucault, and Michelson turned the speed of light into a laboratory constant, measurable with increasing accuracy. The philosophical impact was the rise of precision itself. Nature could be quantified to decimals, and certainty could be manufactured through instruments. The universe was no longer a mystery to be contemplated, but a system to be measured, mapped, and mastered. The cultural faith in science and technology drew power from these achievements, for if light itself could be captured in numbers, then surely all of nature could be subjected to the same discipline. Einstein's special relativity in 1905 shattered the remaining assumptions. By making c the cosmic speed limit, Einstein dissolved the last vestiges of absolutes in space and time. The philosophical consequences were staggering. Time was no longer universal. Space was no longer fixed. Each observer carried their own reality, stitched together by the constancy of light speed. The human sense of simultaneity, of shared moments, was revealed as an illusion. Philosophically, this was as profound as Copernicus displacing Earth from the center of the cosmos. Just as humanity was not central in space, it was not central in time. Reality itself was relative, bound together by light. The 20th century's redefinition of the meter by c pushed the transformation further. Light speed was no longer a property of the world to be measured. It became the definition of distance itself. This was a philosophical inversion. Instead of asking how fast light moved, we now asked how far light traveled in a fraction of a second. In effect, light ceased to be an object of inquiry and became the yardstick of reality. It was as if humanity had surrendered its own artifacts and entrusted the universe to define its measures. The broader cultural shifts cannot be overstated. Navigation, astronomy, communication, all relied on the constancy of c. Philosophers and poets alike reflected on the idea that to see was to gaze into the past, that the universe was always mediated by time. Science fiction writers turned the speed of light into a dramatic boundary, the wall that defined the limits of travel and the structure of causality. The idea seeped into culture, shaping metaphors of speed, knowledge, and limit. Thus, the philosophical journey mirrors the scientific one. Light began as instantaneous and divine, became finite and measurable, and ultimately became fundamental, the definition of time and space. Each transition reshaped not only physics, but the human sense of place in the cosmos. Light was no longer just something we see by, it was something we live by, a constant that defines what it means to move, to perceive, to exist. The transformations of philosophy that came with each shift in light's story continued to ripple outward into culture and human self-understanding. Navigation, for example, was revolutionized by the acceptance of light as finite and measurable. For centuries, sailors had relied on rough star charts, sextants, and mechanical clocks. But once the finite speed of light was recognized and refined into precise catalogues of stellar positions, astronomy became not just a map of the heavens, but a tool for traversing oceans. The correction for stellar aberration that James Bradley had discovered in the 18th century was not a mere curiosity. It was essential to the accuracy of star charts, and with it, navigation itself became more reliable. Here, the abstract notion of finite light reached into the practical fabric of human survival, steering ships safely across the seas. Astronomy itself was reshaped. When rumor revealed that light took minutes to cross the orbit of Earth, humanity realized that the heavens were not what they appeared in the moment of observation. Every telescope was a time machine. To look at Jupiter was to see it nearly an hour in the past. To look at a distant galaxy was to witness an event from millions of years ago. This was a philosophical shock. The sky was no longer a mirror of the present, but a window into history. Human beings had always looked upward for timeless truth, but now they realized they were gazing into memory, the preserved light of things long vanished. Even metaphysics shifted. In antiquity, reality was conceived as immediate and fixed. By the Enlightenment, the realization that light was finite forced philosophers to confront the idea that perception lagged behind reality. The world we saw was not the world as it was, but the world as it had been. The very act of seeing carried with it a built-in deception, a delay that separated consciousness from actuality. For thinkers in the 18th and 19th centuries, this revelation blurred the line between appearance and reality, raising questions about the reliability of human knowledge itself. The 19th century pushed these questions further, embedding them in the culture of science. Precision became a philosophical value in its own right. Fizeau's wheel and Michelson's mirrors were not merely instruments, they were embodiments of a worldview in which truth was to be captured by decimals, refined by repetition, and elevated by certainty. The cultural faith in progress, in the ability of science to conquer ignorance, drew enormous strength from these demonstrations. If the speed of light, once a mystery beyond imagination, could be nailed to the wall with measurements accurate to fractions of a kilometer per second, then surely no secret of nature was beyond reach. Einstein's revolution carried these shifts to their most radical expression. When he declared that the speed of light was the same for all observers, he dissolved centuries of assumptions about absolutes. Time itself was no longer singular, but plural, relative to motion. Philosophically, this was devastating and liberating at once. The idea that there was no universal present challenged deep-seated intuitions about reality. Human beings had to accept that their experience of time was provincial, not cosmic. The universe did not privilege their perspective. It permitted countless perspectives, all equally valid, stitched together only by the constancy of C. This relativization of time carried existential implications. To live was no longer to participate in a single flowing present, but to occupy one strand of a woven fabric, a personal slice of space-time. The consequence was a deep humility. Humanity had been displaced once by Copernicus from the center of the cosmos, and now again by Einstein from the center of time. Light, in its swiftness, had forced both displacements. It became not only a physical constant, but a philosophical one, a reminder that the universe cared nothing for human intuitions of centrality or privilege. By the late 20th century, when C was fixed by definition, the philosophical tone shifted again. Measurement itself had been reoriented. No longer did humans cling to artifacts, rods of platinum, clocks of brass, but instead surrendered their definitions to the constants of the universe. This was a symbolic act of humility and trust. Humanity no longer imposed its own objects upon nature, but allowed nature to define its own standards. The meter became what light declared it to be. The very act of measuring was transformed into an act of aligning human convention with cosmic law. The cultural imagination absorbed these changes. In literature and art, light became a metaphor for limit as well as vision. Science fiction cast the speed of light as the great wall against which ambition dashed, the barrier that made the stars unreachable in a single lifetime. Yet in that barrier lay wonder, for to imagine faster than light travel was to imagine rewriting the laws of causality themselves. Light, once divine and infinite, was now a boundary, both constraining and inspiring, both law and longing. Each philosophical transformation in the story of light built upon the last, and by the modern era, they formed a grand arc of human understanding. What began as speculation about vision and immediacy became a recognition of delay, then a quantification of velocity, and finally, an elevation of light speed into the very architecture of reality. The journey was not just scientific. It altered how humanity conceived of itself and its relationship to the cosmos. In navigation, the finite speed of light made possible technologies that linked the Earth together. From stellar catalogues corrected for aberration to the timing of satellites in orbit, light's constancy became the foundation of global positioning and communication. To find one's place on Earth was, in a sense, to rely upon the universe's most fundamental speed. Where ancient sailors trusted the stars, modern navigators trusted sea, the same constant revealed by Jupiter's moons and Michelson's mirrors. In astronomy, the recognition of delay transformed the sky into a chronicle of the past. Every telescope became a time machine, carrying the human gaze backward through epochs. To see Andromeda was to look across 2 million years. To see the cosmic microwave background was to peer nearly 14 billion years into the universe's childhood. This realization reshaped philosophy itself. The present was no longer universal but local, and the cosmos was not a mirror of eternity, but a history written in photons. Humanity's sense of place shifted from immediacy to perspective, from certainty to humility. Relativity deepened this shift. By making C the limit that bound all observers, Einstein forced the abandonment of absolutes. No single clock ruled the universe. No single ruler measured all. Time was plural, space was pliant, and only the constancy of light stitched them into coherence. The philosophical impact was profound. Human beings, once central in space and then central in time, were displaced once more. Light, not humanity, was the universal measure. Existence itself was relative, framed by the swiftness of light. Culturally, this reorientation left its mark. Writers, artists, and thinkers seized upon the metaphor of light speed as a boundary, an unreachable frontier. In science fiction, it became the limit that defined the possible and the impossible, the horizon that separated imagination from law. In philosophy, it became a symbol of humility, a reminder that the universe was structured by constants beyond human will. And in science, it became the standard of standards, the yardstick by which distance and time themselves were defined. By the end of the 20th century, the story had come full circle. Light had begun as instantaneous, a symbol of divinity and immediacy. It became finite, a messenger that carried the past into the present. Then it became measurable, pinned to decimals by experiment. Finally, it became definitional, the very yardstick of the universe. Each stage reshaped humanity's worldview, carrying us from myth to measurement to metaphysics. The philosophical consequence of this arc is clear. Humanity no longer stands at the center, dictating its measures to the cosmos. Instead, we align ourselves with constants that the universe provides. To measure distance is to follow the path of light. To measure time is to trust the ticking of atoms. To measure reality is to acknowledge that light speed is not only a number, but a principle, a law, a foundation. Thus, the shifts through history are not simply about light. They are about the evolution of human thought itself, the journey from assuming to questioning, from questioning to measuring, and from measuring to redefining. The speed of light, once an elusive mystery, became the constant that revealed the relativity of time, the history of the cosmos, and the humility of human knowledge. In embracing C as universal, humanity embraced a new way of seeing itself, not as the center, but as a participant in a vast, ordered, and astonishing universe. The story of light's speed is the story of how humanity learned to measure the unmeasurable, to define the indefinable, and in doing so, to reshape its vision of the universe. For millennia, light was treated as divine, instantaneous. beyond the grasp of experiment. Philosophers like Aristotle insisted on its immediacy. Medieval thinkers cloaked it in theology, and Galileo strained to catch its delay with lanterns that flickered too slowly for such swiftness. Then old Roma, peering at Jupiter's moons in 1676, dared to say what no one had said before. Light takes time to cross space. His rough estimate of its speed was the first finite measure, the first crack in the illusion of infinity. James Bradley, decades later, found the same truth written in the stars. His discovery of stellar aberration in 1728 revealed that Earth's orbital motion tilted the starlight itself, a subtle displacement that made sense only if light was finite. His calculation matched Roma's, confirming that the cosmos did not reveal itself instantly, but with delay. In that revelation, the heavens became not eternal reflections but histories, their light already aged by the time it reached the human eye. In the 19th century, Fizeau's toothed wheel and Foucault's spinning mirror brought the question home to Earth. No longer did one need moons or stars. In the laboratory, light's flight could be timed, its speed pinned down to numbers within a few % of the modern value. In their experiments, light's swiftness was no longer abstract. It was visible, measurable, written in the flicker of a wheel and the deflection of a mirror. Newton's corpuscles lost their hold. Huygens' waves triumphed. And Maxwell's equations soon wove light into the fabric of electricity and magnetism. Albert Michelson then carried the torch into the age of precision. Across basements, deserts, and mountaintops, his interferometers fixed light's speed with breathtaking accuracy, reducing uncertainty until the constant stood as one of the most reliable numbers in science. His collaboration with Edward Morley failed to detect the ether and open the path to relativity. In his hands, light's velocity became not just a measurement, but a foundation. And then came Einstein, who transformed foundation into cosmos. In 1905, he declared that the speed of light was not merely a number to be measured, but the absolute speed limit of reality. Space and time bent to preserve it, simultaneity dissolved, and energy fused with mass in the equation E equals mc squared. The constant c became more than a swiftness. It became the thread stitching together space-time, causality, and the very structure of existence. By the late 20th century, the pursuit reached its conclusion. Lasers and atomic clocks measured c so precisely that it ceased to be a matter of experiment. In 1983, the meter itself was redefined as the distance light travels in a fraction of a second, and c was fixed at exactly 299,792 kilometers per second. What began as a chase ended in definition. Light speed became the universal yardstick, no longer hunted but enshrined. From the moons of Jupiter to the ripples of space-time, the speed of light has been tested on scales unimaginable to the ancients. Supernovae, pulsars, gamma-ray bursts, and gravitational waves have confirmed again and again that c is constant, unwavering, eternal. The cosmos speaks in its constancy, telling us that causality, order, and relativity rest upon this one unyielding law. Once thought infinite, light revealed itself as finite. Once thought a curiosity, its speed became the measure of all things. Once thought external to the structure of reality, it became the very law by which reality is structured. In teaching humanity that light is not instant but constant, the universe gave us not only a number, but a revelation. To know c is to know that we are creatures in a space-time woven by light, living within limits that give meaning to cause and effect, distance and time, energy and mass. And so the tale closes where it began, with wonder. From the questions of Greek philosophers to the precision of lasers, From Galileo's lanterns to Einstein's relativity, the pursuit of light's speed has been a pursuit of understanding itself. What we discovered was more than swiftness. We discovered the constant that changed everything.